Imagine you're nestled inside a spherical cocoon of light, every point around you glowing with ancient brilliance. This shell is not made of matter, but of time, the faint. Final whispers of photons that began their journey over 13 billion years ago. The stars you see in the night sky are not where they appear. They are ghosts of themselves, frozen in ancient positions by the time it takes their light to cross the cosmos. But just beyond that light, beyond the visible sphere, is something we cannot see, not because it's hidden by dust or distance, but because the laws of causality deny us access. The observable universe ends not in fire or a wall, but in silence. The edge is called the cosmic horizon. More precisely, it is our event horizon, the boundary past which light, even traveling for eternity, will never reach us. This is a limit not of space, but of time and expansion. Space itself is stretching faster than light can traverse it. That means there are galaxies right now, real and vibrant, receding from us so rapidly that we will never, ever see them. Not even a glimmer. And yet, these galaxies are no illusion. They have stars, possibly planets, perhaps even civilizations, asking the same questions we are. But they are separated from us by an ever-growing chasm, a river of expanding space-time that no ship, no photon, no thought can cross. The observable universe, about 93 billion light-years in diameter, is a tiny patch of a universe possibly infinite in extent. It wasn't always like this. There was a time when the universe was young and small, when every galaxy could, in principle, communicate with every other as space aged. It swelled, first slowly, then faster, and now faster still, driven by an unseen force we call dark energy. But to truly grasp what lies beyond this shimmering edge, we must look backward into the layered fossil record of the universe itself. 4 centuries ago, the heavens were thought to be fixed, eternal, and crystalline. The stars were embedded in a great celestial dome. Galileo's telescope cracked that dome open. Copernicus had already moved Earth from the center to the margins of a sun-centered solar system. But even the sun, we learned, was just one star among many. Then, Edwin Hubble peered into the Andromeda Nebula and found it was an entire galaxy outside our own. His measurements revealed more. The galaxies were not just scattered, they were fleeing. The farther away a galaxy is, the faster it appears to move from us. This pattern, Hubble's law, told us that space itself is expanding. Not into anything, not through anything, but expanding in its own right, everywhere, all at once. And as it expands, it carries galaxies with it, like raisins in a rising loaf of bread. This expansion leads us to a paradoxical truth. Although the universe is approximately 13.8 billion years old, the radius of our observable universe is about 46 billion light-years. Why? Because space has expanded during the time that light has been en route. Light from a galaxy that emitted its signal 13 billion years ago has had to chase a moving target. That galaxy is now much farther away than it was when the light began its journey. Like hearing thunder long after the lightning, we're always seeing the universe as it was, not as it is. The light of distant galaxies is stretched into longer wavelengths as they recede, an effect called redshift. At extreme distances, this redshift pushes light into the infrared and microwave parts of the spectrum until it is no longer visible. But those wavelengths still carry meaning. They're records of a universe in its infancy. One such record is the cosmic microwave background, a wall of ancient light, faint and uniform, that surrounds us from all directions. It is the farthest point from which electromagnetic radiation can reach us. The moment the universe became transparent to photons. Before that, it was a seething plasma of particles and radiation, impenetrable like fog. This relic light, discovered accidentally by radio engineers in 1964, offers a snapshot of the universe just 380,000 years after the Big Bang. And yet, even this ancient light doesn't reach the true beginning. The universe before that time is shrouded not just in darkness, but in physical opacity. Our tools cannot yet pierce those early epochs. We infer their properties through models, through mathematics, and through the dance of galaxies that were born from them. Still, beyond every inference lies a question: how much of what we cannot see is real? If the observable universe is a kind of cosmic room, then its walls are drawn not in stone, but in silence. The silence of light that will never arrive. But in that silence may lie the key to something larger than even our most expansive theories can predict. Because if the universe has an edge to what we can know, what lies beyond must be more than an absence. It must be a presence unseen, unmeasured, but no less real. This realization that we are watching a cosmic drama already past, and blind to the current act, invites not despair, but wonder. The horizon is not the end of reality, only the end of our vision. What we know is extraordinary, but what we cannot know may be even more so. 50 million years from now, the light from hundreds of galaxies visible today will have faded past the cosmic horizon, vanishing not because they cease to exist, but because space itself has outpaced the speed of their light. This accelerating separation isn't a rupture in communication. It is the permanent severing of cause and effect. The future, it seems, is a world growing increasingly alone. But if the fate of galaxies is silence, what of the past? How much of Earth's story has been swept away by the same relentless tide of time? Our own planet, solid, ancient, seemingly steadfast, is in fact a master of erasure. Geology is not merely a science of stones, but of memory loss. Every layer that forms atop another buries a chapter of existence, and with enough pressure and time, transforms it into something unrecognizable. Erosion, plate tectonics, subduction, metamorphism. These are Earth's librarians. But unlike human librarians, they do not preserve, they purge. 99.9% of all species that have ever lived are extinct. The same is true for landforms, riverbeds, even whole continents. Our records go back hundreds of millions of years, but they are scattered, fragmented, warped. The fossil record is not a scroll, it is a puzzle, most of whose pieces are missing. Now stretch your imagination back not to the age of the dinosaurs or the rise of mammals, but to 2 billion years ago. The continents had different names, or none at all. The sky was changing, charged with the slow seep of oxygen from newly photosynthesizing life. The great oxidation event had begun, transforming the atmosphere and allowing for energy-rich metabolism. For the first time, Earth was capable of supporting complex life, at least in principle. What if, during this time, something emerged? Not an organism we would recognize, but a civilization. Not a replica of ourselves, but an intelligence adapted to the world as it was: alien oceans, poisonous air, volcanic landscapes. Their technologies might not resemble ours. Their architecture might be molecular, ephemeral, or based on principles we've yet to imagine. And most crucially, what if all trace of them has already been erased? We have seen how quickly the markers of modern society can fade. After 10,000 years, skyscrapers collapse into rubble. After 1 million, even their foundations are dust. After 100 million, any trace is geologically indistinct from background sediment. In 1 billion years, even that is gone, metamorphosed, subducted, or obliterated. The Anthropocene, a term denoting human impact on the Earth, might register as little more than a thin chemical smear in the rock record. To explore this possibility, scientists Gavin Schmidt and Adam Frank proposed the Saluran hypothesis, named after fictional ancient reptilian beings from Doctor Who. Their question was sober. If an industrial civilization had existed in Earth's deep past, what trace would it leave behind? And could we even recognize it? Their answer was unsettling. Many anthropogenic markers, plastics, radioactive isotopes, fossil fuel residues could, in principle, survive as anomalous signatures in geological strata, but these would be ambiguous. Natural processes, such as volcanic eruptions, asteroid impacts, and biogenic activity, also leave complex chemical and isotopic footprints. Disentangling intelligent cause from nature's chaos is, in most cases, impossible. This realization invites a deeper discomfort. What if absence of evidence is not evidence of absence, but merely evidence of nature's capacity to forget? Consider the Oklo phenomenon in Gabon. Here, around 2 billion years ago, natural nuclear fission reactors operated within uranium-rich rocks. They maintained criticality over spans of hundreds of thousands of years, moderated by groundwater that acted astonishingly like engineered cooling systems. Though entirely natural, These formations mimic human nuclear technology so closely that their discovery required deep scrutiny to rule out intelligent origin. Could other such mimics exist? Structures or signals that resemble intelligent design, but are, in fact, geological happenstance. Conversely, could we be dismissing real technosignatures because they appear too irregular, too distorted, too buried beneath our expectations? If a civilization had risen during the Paleo-Proterozoic era, it might have harnessed different resources, geothermal gradients, mineral catalysis, or microbial consortia. Their tools may not corrode, but dissolve. Their monuments may not crumble, but sublimate. Their language may have been inscribed not on stone, but on genomes. And this raises a sharper question. Is intelligence always material? Or can it exist in forms that are networked, distributed, and ephemeral? Could it arise in the form of a sentient microbial mat, or as a superorganism shaped not by brains, but by biochemical signaling? The Cambrian explosion, 500 million years ago, saw an abrupt diversification of complex life. Some biologists propose it was triggered by genetic innovation, oxygen thresholds, or ecological competition. But what if some portion of that innovation was inherited, not evolved? Could a prior intelligence have tinkered with biology, not as a creator, but as a gardener? Such possibilities push the boundary of science into speculation. Yet they also illuminate a blind spot in our thinking. We assume that technological civilizations must resemble ours. But ours is but one path through the forest of possibility. Evolution, constrained by physics and chemistry, still offers infinite forks, and intelligence, like gravity, may be more a property of systems than of forms. We might be archaeologists looking for brick temples in a world that built with wind and magnetism. Paleontologists chasing bones while ignoring neural clouds. Historians of silence. If history teaches anything, it's that intelligence alone does not confer permanence. Civilizations rise not only through insight, but through access to energy, mastery of materials, and resilience against collapse. They fall, almost invariably, through overreach. Complexity grows like a lattice of glass, exquisite, interlocking, and exquisitely fragile. In the story of Earth, complexity always comes at a cost. From bacterial colonies that oxygenated the planet, to mammals building cities, life has reshaped its world at the expense of balance. The more complex the system, the more energy it demands to sustain, and the more prone it becomes to cascading failures. Joseph Tainter, an anthropologist of collapse, once described civilizations as problem-solving entities. Their survival hinges not on simplicity, but on the cost of complexity. Solve one problem, create two more. Layer solutions until the whole structure buckles under its own brilliance. If this is true of us, was it not also true of them? Those hypothetical predecessors lost in deep time. Perhaps they reached the threshold of industrial transformation. Perhaps they altered their biosphere or climate. Perhaps their downfall was gradual, a decoupling of systems, a failure to anticipate feedback loops, or perhaps it was swift, triggered by a runaway technology, a planetary engineering mistake, or a failure to transcend the limits of their resources. If their story ended, it would not be with grandeur, but with diffusion. Cities, if they existed, would have crumbled. Technologies, if material, would have corroded. Genetic codes, if altered, would have drifted. The very memory of their existence would have been overwritten by the slow churn of biology and geology. But here is the deeper dilemma. What counts as a legacy? Is it infrastructure or influence? Traceable artifacts or enduring transformations? We look for ruins in stone, but perhaps the greatest monuments are molecular. A civilization that mastered synthetic biology could leave behind altered organisms engineered to survive, reproduce, and persist. These organisms, over time, would evolve, adapt, diverge, and yet, buried within their DNA, might lie patterns not accounted for by natural selection alone. This idea of a biological message in a bottle echoes in contemporary science. Some researchers have proposed encoding information into the genomes of extremophiles or deep-sea bacteria, theoretically allowing data to persist for hundreds of millions of years. Could something like this already exist? Unrecognized? Could a protein fold, a repetitive gene, or an unexplained evolutionary jump be the echo of a forgotten editor? The Cambrian explosion, with its abrupt surge in morphological diversity, remains a subject of intense debate. While environmental triggers like rising oxygen levels are plausible, some evolutionary biologists note its startling pace and coherence. It is a bloom that seems, from afar, orchestrated, not in the theistic sense, but as if guided by constraints not yet fully understood. Our ancestors were not alone in their complexity. Cephalopods, corvids, cetaceans, each display cognitive sophistication rivaling that of primates. And yet, none built cities, crafted metallurgy, or altered planetary chemistry. The leap from intelligence to technology is not inevitable. It is a rare convergence biology, environment, resources, and perhaps a moment of cultural alignment. And even then, it may be fleeting. What if the story of intelligent life is not a linear ascent, but a cycle? Intelligence arises, transforms its world, and disappears, leaving behind only the conditions for life to begin again. A kind of planetary reset, not of apocalypse, but of forgetting. And in each cycle, the forms change, but the limits remain. Thermodynamics is not just a law of machines. It is the boundary of civilization itself. Every process that sustains us, manufacturing, computation, agriculture, produces entropy, waste heat, structural decay, informational loss. Even in the most efficient systems, disorder grows. If a civilization cannot outrun entropy, it must simplify, decentralize, or collapse. Here lies the paradox to grow in power. Intelligence must increase complexity, But complexity demands energy, and energy demands extraction, transformation, and risk. The more sophisticated a society becomes, the narrower the path it walks between flourishing and implosion. This isn't pessimism, it's physics. Now consider this: if a prior civilization confronted these same constraints, might they have chosen a different path? Instead of growth, perhaps they pursued integration. Instead of expansion, introspection. A technological inwardness, quiet, minimal, resilient. Imagine a civilization that, recognizing the limits of sustainability, opted to embed itself into the biosphere, to hybridize with microbial ecosystems, to encode memory in symbiotic genomes. Its greatest structures may not have been visible. Its intelligence may have dispersed into mycelial networks, oceanic layers, or magnetotactic bacteria. To us, they would seem like nature itself. Such a society would not leave monuments, but perhaps it would leave patterns, disruptions in genetic entropy, anomalies in microbial evolution, signals nested in biodiversity itself. This is not fantasy. Modern synthetic biologists already engineer microbes that glow in response to toxins, fungi that produce enzymes on demand, algae that compute with biochemical logic. Scale this up by a few million years of innovation, and you could sculpt ecosystems with purpose, without a single visible artifact. The ocean then becomes not just the cradle of life, but its hidden archive, beneath thousands of meters of water, where light never reaches and tectonic churn is slower. Records may remain sediment cores preserving molecular fossils, isotopic shifts, or biochemical markers of past manipulation. But we must be careful not to see intention where there is only chance. Nature is capable of creating false positives. A hexagonal basalt column is not a pillar. A mineral inclusion is not a circuit. A genetic duplication is not always design. And yet, among these false positives, might there be a signal we've dismissed too quickly? A recurring anomaly, a persistent irregularity in evolutionary logic. To read such a signal, we must first admit our expectations may blind us. We look for civilizations with fire, metallurgy, wheels, and cities. But intelligence may wear other masks: fluid, decentralized, encrypted in life itself. Perhaps the question is not, where are they, but what are we not seeing? The search for intelligence, both past and present, too often starts from the presumption that it must resemble us, that it must climb the same ladder of invention: fire, tools, machines, networks, leaving behind artifacts of metal, stone, or plastic. But intelligence may express itself in ways that do not produce ruins, in ways that do not command architecture, but rather dissolve into ecosystems or fold into the logic of a planet's self-regulation. If a prior intelligence once occupied Earth, its traces might be more like ghost signatures in climate records than statues in sand. The planet's deep time memory lies not not in the preserved shapes of its inhabitants, but in the isotopic fingerprints of what they changed. Consider the Paleocene-Eocene thermal maximum, a dramatic spike in temperature 55 million years ago. The carbon isotope excursion left behind during that time suggests a rapid and massive release of carbon into the atmosphere, perhaps as much as 5,000 gigatons. Some scientists believe it was caused by the destabilization of methane hydrates triggered by volcanic activity. But others wonder if the trigger was not a one-time geologic event, but a system in overshoot, a biosphere reacting to stress, or perhaps an unseen agent with the means to alter it. This is not to say such anomalies prove intelligence, but they remind us that the Earth is a reactive system. Disturb it deeply enough, and it responds. And if intelligence is part of that disturbance, if it becomes an agent that reshapes the chemistry of oceans or the behavior of the carbon cycle, it leaves behind a mark more enduring than any monument. The most enduring legacy of our own civilization will not be our architecture or our data. It will be the changes we've made to the Earth system. Ocean acidification, altered nitrogen cycles, a global redistribution of biomass, a spike in radiation signatures from nuclear testing, a new sedimentary layer of plastics. These are technofossils, not of things we've built, but of effects we've caused. So if we wish to find echoes of a former intelligence, perhaps we must think less like archaeologists and more like climatologists, chemists, evolutionary theorists. Instead of looking for temples, we should look for irreversibilities. The record of such irreversibilities lies in rocks, in ice, in deep sea cores. It is there we may one day find not the tool, but the footprint of cognition, an anomaly in the rhythm of carbon, a break in the expected pathways of nitrogen, a rearrangement of trace metals far too ordered for chance. This idea underpins the Saluran hypothesis not as proof, but as a thought experiment with teeth, proposed by climatologist Gavin Schmidt and astrophysicist Adam Frank. The hypothesis asks, would we even know if there had been a technological civilization tens or hundreds of millions of years ago? What would they have left? What signals might persist? Their conclusion, very few. Geological time is not a neutral archive. It is a risker. Subduction consumes continents. Erosion wears down all things. Metamorphism erases chemistry. Even the best preserved sediments offer only a brief whisper before they are folded, crushed, or melted back into the planet's interior. This geological amnesia has consequences. It means we are always reconstructing the past with fragments less a jigsaw puzzle than a burnt manuscript. We infer civilization by the statistical improbability of order, a regular pattern, a structure beyond randomness. But natural systems can create such patterns too. The dance of minerals, the logic of crystallization, the flow of lava and water, which carve order into chaos. This ambiguity demands rigor, but it also demands humility. We cannot ask the earth simple questions and expect simple answers. If we ask, Did another civilization come before us? We must be ready for replies that do not come in clear words, but in the form of layered sediment, isotopic noise, or genetic stutter. Consider again the natural nuclear reactors of Oklo in Gabon, discovered in the 1970s. These ancient uranium deposits underwent sustained nuclear fission 2 billion years ago. The reaction was moderated by groundwater, forming a self-regulating cycle. The isotopic residues are indistinguishable, in some ways, from what a modern reactor might leave behind. Yet we believe these were natural because the geology, the chemistry, the environmental conditions all align to make such a process plausible. Still, we return to the same haunting possibility: if nature can imitate engineering so well, might engineering sometimes resemble nature? The challenge, then, is not just to find anomalies, but to develop a methodology for distinguishing intelligence from accident, a forensic geology, a science of deep time cognition. One promising approach is to look for technosignatures in isotopic ratios, artificial enrichments, or depletions that resist natural explanations. For example, unusual ratios of uranium isotopes, or the presence of isotopes that decay too quickly to be natural unless continually replenished. Another approach is to look for materials that don't form naturally at all: complex alloys, synthetic polymers, or molecular arrangements that require controlled conditions to produce. But here's the paradox: our own civilization, though global and technologically advanced, might leave almost none of these things after 100 million years. Metals corrode, concrete fractures, plastics decompose under heat and pressure. Even radioactive waste may become undetectable if the surrounding minerals reabsorb the isotopes. The best place to preserve artificiality might not be on Earth at all. Structures on the Moon or satellites in stable Lagrange points could theoretically survive for billions of years. But even in space, micrometeorite erosion, radiation damage, and orbital decay impose limits. A single century of orbital neglect has already created a shell of space debris around our planet. Project that forward by millions of years, and most of it is gone, pulled into the atmosphere, or shattered into pieces too small to detect. Still, a true relic might remain hidden in the regolith of a crater, buried in a cave, shielded from erosion. Perhaps not a machine, but an information artifact, an object with low entropy and high order, something that, by its very improbability, implies intentionality. And yet the most tantalizing possibility remains: this, the signal, may be biological. A civilization that learned to code in DNA might have embedded messages into the genomes of long-lived organisms, lichen, spores, extremophiles, information stored in base pairs, a literal language of life. There is even speculation among bioinformaticians that certain non-coding regions of the human genome, the so-called junk DNA, could, in principle, carry arbitrary information, patterns without a known function, sequences that resist mutation, not because they confer an evolutionary advantage, but because they were designed to endure. But how would we ever decode such a message? It would require not just translation, but recognition. We would need to see the intent behind the structure, to distinguish signal from statistical coincidence. And we would need to understand the mind that encoded it, its logic, its metaphors, its language of thought. This brings us to the edge of epistemology. What are the limits of what we can know if intelligence comes in forms radically different from our own? Biologically, cognitively, technologically, can we recognize it at all? Carl Sagan once said, "Absence of evidence is not evidence of absence." But he also warned that extraordinary claims require extraordinary evidence. The Saluran hypothesis does not claim ancient civilizations existed. It merely reminds us that our certainty of their absence rests on surprisingly thin ice. And it dares us to ask, what are we not seeing? Because we're not prepared to look. In the end, the search for deep time intelligence is not just a scientific endeavor, it's an act of imagination, a way to think about the limits of knowledge, the nature of memory, and the fragility of legacy. And perhaps it's also a mirror. In asking what might have come before, we ask what might remain of us. What will be our technofossils? What will be our irreversibilities? Or will the Earth, in time, erase us just as cleanly? The deepest silence is not the absence of sound, but the fading of memory. And in cosmic terms, memory is always at risk, not only from erosion and time, but from the accelerating expansion of space itself. What begins in vivid light ends in red-shifted whispers. The voices of stars, the breath of galaxies, the artifacts of thought all stretch toward oblivion. But perhaps the final silence is not a void, but a veil. Beyond it, there may be something more hidden, not by distance or scale, but by cognitive boundary. If another intelligence existed before us, whether here on Earth or far beyond it, might not be gone, only unread. And the unread can still be discovered. What if human civilization is not an origin story, but a restart? Not the first spark of awareness, but the rekindling of a flame once lit by other minds, extinguished, then reignited in a new epoch, with new tools, new forms, but the same fundamental curiosity. This would mean that consciousness is not a fluke, but a feature, a recurring property of complex systems, emerging wherever the conditions are right. Like gravity, it would not need to be invented, only discovered. Like mathematics, it would not belong to us, only pass through us. The stars may know this. They have watched entire generations of galaxies form and fade. In their fusion and fire, they create the elements that build life. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes the chemistry of complexity. And from that complexity, the possibility of cognition. In this sense, every star is a seed, not of life directly, but of the potential for it. And every planet with liquid water, stable orbit, And geological energy is a crucible. On some of these worlds, perhaps, life did not just arise, it awoke. If consciousness is inevitable, then we are not alone. Not in space, not in time. And if civilizations rise and fall in cycles, their messages may not be in machines, but in memory coded into genomes, climate cycles, or even planetary behavior. We may not be their descendants by biology, but by pattern, by echo. The Earth itself may be the message, its resilience, its scars, its rhythms. Like a palimpsest rewritten with each epoch, bearing ghost traces of every prior inscription. There are even those who speculate that planets can behave like organisms, self-regulating, adaptive, resilient. James Lovelock's Gaia hypothesis once proposed that life and the Earth co-evolve, stabilizing one another through feedback loops. If a civilization became sufficiently integrated with its world, its intelligence might no longer be distinct from the biosphere. It would be everywhere and nowhere. It would leave no ruins, but it would guide planetary evolution. Perhaps then, the goal of civilization is not expansion, but assimilation, not to conquer nature, but to become invisible within it. A kind of ultimate camouflage, not from enemies, but from extinction. From this perspective, the failure to find extraterrestrial intelligences is not due to their rarity, but their restraint. The loudest civilizations may burn brightest and briefest. The wisest may be the quietest of all. And maybe we are not yet wise. We broadcast our presence in radio waves. We launch plaques and probes into the void. We scrape, mine, burn, and accelerate, always faster, always more. Our memory is short, our systems fragile, but our curiosity is fierce. So we look outward. We search for exoplanets. We scan the sky for technosignatures. We measure starlight for artificial dimming. Seek Dyson spheres. Listen for beacons. And while we find none, we do not stop. But perhaps the greatest search is inward. What is the nature of thought, of experience? What do we mean by intelligence? And how would we recognize it if it came to us not in a form, but in a frequency? Not in a message, but in a method? What if intelligence is not a thing, but a way of relating a process that arises whenever systems become sufficiently aware of themselves and their surroundings? Then the trees, the oceans, the weather patterns, even cells and circuits might carry fragments of that awareness, not as fiction, but as function, as information, organized and exchanged. In this view, we are not separate from the story. We are the continuation of it. Every discovery, every mistake, every act of learning extends the arc of that unfolding. Whether we endure or disappear, we are part of something vast. Not a narrative of domination, but of emergence. And so we return to the question, what remains? Not stone or steel or signal, but understanding. The recognition that we are temporary custodians of memory, meaning, and possibility. That our actions ripple not only into space, but into time. In the end, the legacy of any civilization may be not what it built, but what it enabled. If we can learn from the silence, if we can find humility in the gaps, vision in the shadows, we may leave behind something truly extraordinary. A future worth remembering. A silence not of absence, but of depth. And the quiet promise that even in forgetting, the cosmos remembers how to dream again.
A telescope, still warm from a craftsman's hands, glinted under the flickering lamplight in a London attic. Through its lens, the night bloomed with a startling complexity. The stars, once eternal fixtures of divine narrative, now shimmered as unresolved questions. When William Herschel trained his eye through that lens, he saw not just stars, but whole systems whose very light had begun its journey before human history had written its first verse. At that moment, something ancient unraveled. The cosmos was no longer a painted dome, but a sea of structures, unbounded in their number and their scale. And yet, for all its poetic allure, astronomy after Newton moved slowly. The laws of motion and gravity had been declared, but the instruments needed to test their implications across the heavens were still crude. Telescopes lacked precision. The photographic plate and the spectroscope tools that would later revolutionize how we decipher the light of stars had yet to be applied to the sky. The 18th and 19th centuries were marked not by the rapid conquest of the stars, but by a long, methodical awakening. Beneath those incremental advances lay the stirring of deeper questions. What were the nebulous smudges in the night sky? Were they clouds of gas, unresolved clusters of stars, or perhaps entire galaxies too distant for even the sharpest eye? The distinction was not semantic. Embedded in it was the tension between two worldviews, one that imagined a single galactic system, an island cosmos, and another that dared to envision an endless archipelago of galaxies scattered through infinite space. Thomas Wright of Durham, in his 1750 book, An Original Theory of the Universe, proposed that the Milky Way was not a chance scattering of stars, but a structured entity. He imagined it as a ring or spherical shell of stars, with a divine center, a kind of gravitational sanctuary of cosmic grace. Wright went further, speculating that the nebulae seen faintly through telescopes were other Milky Ways, other creations spinning in the depths. His ideas struck a chord with a young Immanuel Kant, who absorbed Wright's vision and re-articulated it in more rigorous, secular terms. Kant described the Milky Way as a rotating disk of stars, bound by gravity, and posited that the hazy patches of light across the sky were analogous systems galaxies. He imagined a grand hierarchy, stars clustering into galaxies, galaxies into clusters, clusters into superclusters. It was an intuition that prefigured our modern understanding of large-scale structure. But to Kant, it was more than structure, it was metaphysics. Infinity, for him, was not merely unending space, but the exhaustion of the imagination itself. As telescopes improved, these early metaphysical musings began to confront empirical resistance. Astronomers like William Herschel turned observation into cataloging. He and his sister Caroline charted thousands of stars and nebulae, peering deeper than anyone before. At first, they assumed that all stars were suns like our own, evenly distributed, and that dimmer stars were simply more distant. These assumptions shaped a model in which the Milky Way was a flattened disk with the Sun near its center. But one by one, those assumptions failed. Obscuring clouds of interstellar dust masked vast regions of the galaxy. Star brightness varied immensely, and space was anything but uniformly populated. Herschel's belief that starless regions were holes in the sky, windows into the void, was, in retrospect, an early misunderstanding of cosmic dust. But his intuition that nebulae might be island universes similar to the Milky Way proved prescient. Over time, even Herschel grew skeptical of his initial certainty. Some nebulae, he noticed, looked like glowing fluids rather than star clusters. Others remained obstinately unresolved even under the best telescopes. Still, the dominant view in the 19th century, especially in Victorian cosmology, was conservative. Agnes Clerk, a respected chronicler of astronomy, wrote in 1890 that no competent thinker could suppose a nebula to be a separate star system. The galaxy, our galaxy, was the universe. Beyond it lay darkness, mystery, or perhaps the throne of God. This was the culmination of a one-island vision, steeped in the old Stoic model but now dressed in atomic theory and Newtonian mechanics. And yet, cracks in the Victorian universe had begun to form. Spectroscopy, the science of dissecting light, was making the heavens chemically knowable. William Huggins, aided by his wife Margaret, used this tool to compare starlight with elements tested in laboratories on Earth. When he aimed his spectroscope at a planetary nebula in Draco and saw not a spectrum of stars but emission lines characteristic of glowing gas, the revelation was seismic. The nebula was not a star cluster, it was a cloud of hot gas, confirming Laplace's old hypothesis that solar systems could form from collapsing gas clouds. The light itself had become a messenger. In its colors and lines was written the nature of distant matter, its composition, temperature, and even motion. With the advent of the Doppler effect, astronomers could measure the radial velocity of stars. Those moving toward Earth showed a blue shift in their spectra, those receding, a red shift. Space had begun to move, but light carried another, subtler message. It traveled at a finite speed, 300,000 kilometers per second. This meant that every glance skyward was a glimpse into the past. When Herschel said his telescope reached back 2 million years, he wasn't speaking metaphorically. Light became time, and space became memory. The stars were not as they are, but as they were. In this way, cosmology became not only a science of structure, but a chronicle of ancient light. By the late 19th century, the fusion of physics and astronomy, what would soon be called astrophysics, had reshaped our understanding. Yet one riddle remained unchanged and unresolved. Why is the night sky dark? If the universe were infinite and eternal, filled uniformly with stars, then every line of sight should end in a star, and the sky should blaze with light. This paradox, sometimes called Olber's paradox, haunted cosmology. Victorian scientists explained it by invoking a finite universe, where stars did not extend infinitely, and space eventually ran out. But other possibilities, some more radical, lurked beneath the surface. Hierarchical models returned. Scientists such as Fournier Daub and Carl Charlier revived the notion of fractal universes, structures in which stars clumped into galaxies, galaxies into clusters, and so on. If the density of matter decreased fast enough at larger scales, the night sky could remain dark, even if the universe were infinite. In such a universe, space wasn't empty. It was textured, recursive, and perpetually unfolding. From deserts and oceans, where light pollution does not dilute the sky's message, the Milky Way arches overhead like a silent script to those who once navigated by its light or prayed beneath its glow. The night sky was not a question, it was an answer. But to the minds awakened by physics and philosophy, it became something else entirely, a boundless riddle. The modern cosmos, just beginning to reveal itself by the end of the 19th century, had grown too vast, too intricate to be reduced to allegory. Stars no longer twinkled in a perfect crystalline dome. They orbited black holes, collided, exploded as supernovae, and whispered their stories across billions of years through the slow, persistent drift of photons. The telescope had become a time machine, the spectroscope a chemical translator, and the sky a record of ancient and future truths. But what if this record, in all its grandeur, was only the surface? Beneath the elegance of law and spectrum lay something stranger still, a universe not merely vast, but recursive, not just old, but entangled with our perception of time itself. In the flicker of a candle, light leaps from the flame and travels outward unstoppable, weightless, untouchable. It moves across furniture, reflects from bookshelves, glances off the curve of a teacup, and eventually fades into walls or windows. But in space, it does not fade. It stretches. It remembers. Long after its source has changed or died, light carries a ghost image, a final photograph, frozen in flight, frozen in. For centuries, humanity misunderstood the implications of light's speed. Even as the waves and particles of light were debated, its velocity finite, calculable, and constant remained a footnote rather than a compass. The discovery by Ola Romer that Jupiter's moons appeared delayed when Earth moved away from them was more than a triumph of measurement. It was a mirror turned on time itself. Once the finite speed of light was accepted, a new, profound realization emerged. To look at the stars was to look back into history. Each twinkle in the night sky was a story from the past, a message delayed by the tyranny of distance. A nearby star might send its greeting from a few years ago. A distant galaxy spoke in million-year-old syllables. The edge of the visible universe offered whispers from near the beginning of time. Space became a layered archive, where depth was synonymous with age. The further out astronomers looked, the younger the universe appeared, not because of evolution, but because of delay. The observable universe, then, was not a structure in space, but a cone in space-time, widening backward, filled with shadows of everything that once was. This changed everything. The Victorian universe, still dominant in public imagination, envisioned the cosmos as a tidy estate, a single galactic mansion set amidst a black, windless sea. It was an elegant model, centralized, comprehensible, divine. But as astrophysics advanced, that mansion began to collapse under its own philosophical scaffolding. Darkness itself became a clue. The absence of light between stars was not just empty space, it was evidence. In an eternal, infinite universe filled with stars, there should be no darkness. Every part of the sky should be saturated with starlight. Yet we have night. This was not merely a poetic paradox, it was a physical one. Solutions emerged. One argued that light from distant stars was absorbed by interstellar dust, but dust, too, would eventually heat up and re-radiate, defeating the argument. Another said that the universe had a finite number of stars, or that it was simply not old enough for their light to have reached us. These solutions leaned on time, not space, as the limiting factor. In essence, the night sky was dark because the universe had a beginning. If light is time's courier, then the cosmos is not a space through which light travels, but a tapestry woven by that journey. Observing a galaxy 10 billion light-years away is not to see it 10 billion kilometers distant, but 10 billion years old. It is to see it not where it is, but where it was. The notion that we are seeing the universe as it truly is collapses under this realization. We are witnesses to a memory, stitched together from radiant fragments. And if light encodes time, what does that say about the thermodynamic arrow, the inexorable drift from order to disorder, from low entropy to high? In the 19th century, thermodynamics emerged as a powerful framework for understanding the physical world. Entropy, once a mathematical abstraction, became a fundamental measure of cosmic direction. The universe is not static. It is a machine that runs down. Stars burn their hydrogen. Galaxies drift apart. Entropy increases, and with each increase, information is lost. Configurations become less reversible, and the clarity of structure gives way to the haze of equilibrium. If time has a direction, it is not just because clocks tick forward, but because entropy dictates an irreversible march toward disorder. This posed a devastating question. Is the universe dying? Heat death, the ultimate state in which all usable energy is exhausted, and no work can be performed, emerged as a prediction grounded in thermodynamic law. The stars would fade, the galaxies would dim, and the cosmos would become a thin, cold mist of particles and radiation. Nothing could escape this fate, because physics itself had spoken. Yet even in that bleak prognosis, human thought refused surrender. Hierarchies were imagined nested universes, fractal arrangements of stars and systems, each level containing the seeds of another. Some scientists wondered if our universe was itself the product of a larger system's entropy, the cast-off heat of a higher-order event. In 1952, Walter Baade helped resolve a lingering inconsistency in cosmology. It had appeared that our galaxy was too large compared to others too grand, too exceptional. By differentiating between two types of stars, population 1, young and metal-rich, and population 2, old and sparse, he corrected distance calculations. The Milky Way was no longer bloated in the cosmic census. It had been mismeasured. The stage was reset. Meanwhile, another kind of light cosmic background radiation was theorized. If the universe began in a hot, dense state, there should be a relic glow, cooled by expansion, bathing all of space. It would be ancient, uniform, and isotropic. And though this radiation had not yet been observed, its theoretical fingerprint began to shape cosmological thought. We were now chasing the afterimage of a beginning, not a metaphysical genesis, but a physical explosion, the Big Bang. The term was coined in derision, but it stuck, because it named something tangible, a universe with a past, a trajectory, and a thermodynamic gradient. A universe whose history could be measured, not merely imagined. If darkness at night revealed the universe's youth, and spectral shifts revealed its motion, then entropy revealed its direction. These were not just scientific insights, they were revolutions in ontology. The universe was not a container, it was a process. To measure time is to measure change, and to measure cosmic time is to watch change unfold not in seconds or centuries, but in epochs, the cooling of plasma into atoms, the birth of stars from interstellar clouds, the assembly of galaxies from primordial filaments. Each layer of light is a fossil, and the cosmos is a museum lit by photons that have not yet caught up with the present. But perhaps most haunting is this: the present itself is always slipping. The light we see, even from the moon, is old. The sky above is not the sky now. It is the sky then. The observer stands in a now that is never truly synchronous with the observed. Reality is stitched from delay. If this seems like a metaphysical trap, it is. And yet, it is a trap of our own, making a byproduct of insisting that knowledge must mirror simultaneity. The universe does not care for such symmetry. It offers instead a different kind of truth that time and light, entangled, give us not the universe as it is, but as it was, across 1,000 scales and stories. In this way, astronomy became biography of stars, of systems, of space itself. Each photon that reaches Earth is a fragment of a narrative written in distance and decay. It is a messenger from a version of the universe that no longer exists. And what, then, of us? We stand in the middle of this great glowing cone of delayed light. We are the last recipients of stories written billions of years ago, and with our own telescopes, equations, and minds, we write new stories, extrapolations, hypotheses, maps of meaning drawn not from presence but from echo. The universe does not whisper its secrets. It shouts them across the abyss, in wavelengths and spectra, in curvature and cold. But to hear it, one must listen not to the sound, but to the silence between, where time waits in the stillness of old light. A falling apple did more than draw Newton's gaze. It inaugurated a vision of the universe as clockwork, a world where force reigned, vectors directed, and mass obeyed. Gravity, for Newton, was an invisible tug, instantaneous and universal. Every object pulled on every other object, not through ropes or levers, but across the nothingness of space. And yet, that space, absolute, immutable, and eternal, was an assumption. Time, too, was treated as a fixed backdrop, ticking uniformly for all observers. This scaffolding served well for 2 centuries. It let planets be predicted, comets be tracked, and tides be tamed. But it failed to ask a more haunting question: what if the scaffolding itself was dynamic? In the early 20th century, Albert Einstein took this question seriously. He didn't just ask what space and time contained, he asked what they were. And what he discovered shattered the illusion of a passive cosmos. In 1915, Einstein presented the general theory of relativity. At its heart was a radical claim: gravity is not a force, it is geometry. Mass and energy, he said, warp space-time. And space-time tells mass how to move. The apple falls not because the Earth pulls it, but because it follows the straightest path through a curved 4-dimensional reality. This path, a geodesic, is not imposed by force, but by shape. To accept this is to abandon intuition. It is to imagine Earth orbiting the sun, not as a rock pulled by tether, but as a marble spiraling along a curved sheet. And this curvature, gentle at planetary scales, becomes extreme near neutron stars, black holes, and the core of collapsing galaxies. Light, too, obeys this curvature. It bends around massive objects, its path deflected by the invisible wells of geometry. This prediction gravitational lensing was confirmed during a solar eclipse in 1919, when starlight grazing the sun was seen to shift, its apparent position displaced by the sun's invisible grip on space-time. The universe had become elastic. Space was not a void, but a participant. Time was not universal, but local. Events no longer unfolded simultaneously for all observers. Simultaneity had fractured. This shattered the absolute time of Newton and replaced it with relational time. Clocks on satellites tick differently than those on Earth. Signals from pulsars arrive warped by the gravitational wells they pass through. Even aging becomes relative faster in weaker gravity, slower near massive bodies. These are not metaphors. They are engineering constraints in our GPS systems and scientific lifelines in black hole research. If general relativity reshaped how we understood gravity, it also redefined cosmology. Instead of static, the universe became dynamic. Space could stretch, time could accelerate, entire volumes of the cosmos could evolve, not in isolation, but as part of a single, mutable continuum. This conceptual leap revived a long-dormant question: had the universe always existed? The mathematics of general relativity suggested otherwise. Solutions to Einstein's equations implied that the universe might be expanding. If so, it must have once been denser, perhaps infinitely so. A beginning loomed, not a mythic origin, but a boundary condition in space-time, a singularity where density, temperature, and curvature reached unimaginable extremes. In 1927, Georges Lemaître, a Belgian priest and physicist, proposed what would become known as the Big Bang. The universe began as a primeval atom, exploding outward in a great unfolding. His model was met with skepticism. A dynamic cosmos clashed with the still cherished image of an eternal one. Yet data began to accumulate. Edwin Hubble, using observations of distant galaxies, showed that their light was redshifted, stretched toward longer wavelengths, as if they were moving away. The more distant the galaxy, the greater its redshift. Space itself was expanding, not the galaxies within it. This wasn't movement through space. It was the growth of space itself. The Doppler effect had matured into cosmological redshift, and the expansion of the universe was no longer hypothetical, it was measurable. Einstein, who had initially introduced a cosmological constant to preserve a static universe, reportedly called its inclusion his greatest blunder. Reality, it turned out, favored expansion. And yet, what was expanding? Not into anything, but within itself. The fabric of space stretched like dough rising in an oven. No edge, no center, no outside. Every point receded from every other. To live in such a universe is to inhabit a paradox. Everything moves apart. Yet no one place is privileged as the point of divergence. This expansion rewrote the meaning of distance. A galaxy a billion light years away is not a billion years old. It is the remnant of what that galaxy once was, its light diluted and delayed. And due to the stretching of space, it may now be far beyond what its original position implies, perhaps unreachable, perhaps already gone. The observable universe, then, is a horizon, not a limit of what exists, but of what we can know. Beyond it, light has not yet reached us. Those realms are not inaccessible by geography, but by history. The boundary of the visible is not a wall, but a clock. Cosmic time, now formalized as look-back time, gives us a history in layers. From the cosmic microwave background, a relic glow from when atoms first formed, to the faint blue galaxies at the farthest edge of detection. We see a universe in adolescence, youth, and infancy, and we see it all at once, embedded in space. This time mosaic forces a rethinking of ontology. In daily life, objects coexist: a table, a bird, a voice. But in cosmology, coexistence dissolves. The galaxy we study might no longer exist. Its light is an obituary arriving late. Every astronomical photograph is both presence and absence, both now and then. The observer, once assumed to be detached, becomes central. We do not merely observe the universe, we slice it with our moment. Each redshift, each photon, each measurement is a dialogue between the present and the past. What then is reality? In general relativity, reality is not static. It is foliation, a sequence of spatial slices, each tied to a moment in time, each observer seeing a different cut. There is no single universal now. Each vantage point carries its own temporal frame, its own truth. This is not merely physics. It is philosophy reborn in empirical form. The ancient arguments of Zeno, Plato, and Kant about motion, perception, and causality are no longer abstract. They are measurable in the drift of satellite clocks and the arc of starlight around gravity wells. Einstein's equations, intricate and symmetrical, do not only describe stars and planets, they describe the architecture of causality. What can influence what? What can escape? What remains forever hidden behind horizons? Nowhere is this clearer than in the concept of a black hole. When a massive star collapses, its escape velocity exceeds the speed of light. Nothing, not even photons, can flee. From outside, the star seems to freeze at its event horizon. But inside, space-time continues. The center becomes a singularity, where curvature becomes infinite and our laws of physics unravel. To enter a black hole is to cross a threshold not of space, but of determinism. The known becomes unknowable. The fabric of reality folds inward, and time becomes space, and space becomes time. The metaphors fail because the geometry does not obey human intuition. But the equations persist. And so, we find ourselves at a precipice. The universe is not a static theater in which events unfold. It is the unfolding. Its shape determines its story, and its story, rich in curvature and consequence, invites not just understanding but awe. Yet awe, too, must evolve. No longer the awe of immensity alone, but of structure, not of size, but of interrelation. Awe, now, belongs to the realization that our universe is a fabric stitched by energy, shaped by mass, curved by presence, and illuminated not by metaphor, but by mathematics. And still, one question remains: if space can stretch and time can bend, what is the ultimate shape of everything? Not in volume or contour, but in causality, in logic, in the possibility of knowing. The next chapter, then, must unfold not just outward, but inward, toward the human mind that maps such things, and the principles that shape its vision of the cosmos. Imagine a speck smaller than a proton, hotter than the core of any star, denser than all matter in the observable universe combined. Now imagine that speck not suspended in space, but being space itself, not in time, but being the origin of time. This is no allegory. It is the leading hypothesis for how our universe began. According to the Big Bang model, the early universe was not a place inside which things happened. It was the happening, a turbulent eruption from a singular point where the known laws of physics, derived from general relativity and quantum mechanics, ceased to cohere. Yet this beginning is not the explosion of classical imagination of debris flung outward into emptiness. There was no outside. What expanded was the metric of space itself. Every inch, every atom, every particle of vacuum raced away from every other in a moment of unfathomable inflation. Inflationary cosmology, proposed in the early 1980s by Alan Guth and others, addressed persistent mysteries in the standard Big Bang model. Why is the universe so smooth on large scales, despite being causally disconnected in early epochs? Why is it so flat, neither curling in upon itself nor expanding chaotically? Why do we not observe magnetic monopoles, hypothetical relics predicted by high-energy physics? Inflation answered these with one sweeping gesture, a phase of exponential expansion in the first tiny fraction of a second. Driven by a field called the inflaton, space grew by a factor greater than 1060 in less than 10 to 35 seconds. Quantum fluctuations during this inflationary burst were stretched across cosmic distances, seeding the structure we now observe as galaxies, clusters, and voids. These fluctuations left imprints on the oldest light in the universe, the cosmic microwave background, a faint bath of radiation released when the universe cooled enough for atoms to form and photons to travel freely. First detected in 1965, the CMB became our Rosetta Stone for early cosmology. Its slight temperature variations encode the universe's initial conditions, now mapped with stunning precision by satellites like COBE, WMAP, and Planck. And here, in the afterglow of creation, quantum mechanics whispers across cosmological scales. The uncertainty principle so familiar in particle physics finds its cosmic avatar. Minute energy jitters in the quantum vacuum, once confined to the subatomic world, were amplified by inflation into the architecture of the universe. Galaxies are, in essence, quantum shadows magnified by gravity. But with inflation came a deeper riddle. The inflaton field, like other quantum fields, does not behave identically everywhere. It undergoes fluctuations. In some regions, it decays and reheats space into particles and radiation. In others, it continues to inflate. This leads to eternal inflation, a process in which inflation ends in pockets bubble universes while continuing elsewhere. Each bubble becomes a universe with its own laws, constants, and particles. Thus emerged the concept of the multiverse. Our universe may be one island in an infinite archipelago, not metaphorically, but mathematically. A single field's stochastic decay can yield an ensemble of outcomes, each causally disconnected from the next. Some may be sterile, others, like ours, may birth stars, chemistry, and observers. The anthropic principle, once a fringe idea, is now discussed as a selection effect. We observe this universe because it permits observation. Yet many recoil from this vision. It smacks of resignation. It risks replacing explanation with happenstance. If everything exists somewhere, do laws mean anything at all? These are not idle questions. They pierce the boundary between physics and philosophy. The multiverse is not directly observable, at least. Not yet. It cannot be tested in the way traditional theories can. And so, it straddles the uneasy zone between science and metaphysical speculation. But the implications are staggering. The constants of nature, the strength of gravity, the mass of the electron, the cosmological constant may not be fundamental, but environmental. They may vary across the multiverse like humidity varies across Earth. And we, delicate arrangements of carbon and time, may be tuned not by design but by necessity. If gravity were stronger, stars would collapse too quickly. If electromagnetism differed slightly, chemistry would fail. If the vacuum energy were higher, galaxies would never have formed. We teeter on a knife edge, balanced by parameters that, in the multiverse view, are neither rare nor chosen just local. Still, we ask, does a theory that predicts everything explain anything? Quantum cosmology wrestles with this. It seeks a framework in which the universe itself is described by a wave function, a superposition of possible geometries, matter distributions, and histories. In the Hartle-Hawking no-boundary proposal, the universe has no edge in time, just as Earth has no edge in latitude. It begins not with a singularity, but a smooth emergence from a quantum fuzz. In such models, the laws of quantum mechanics apply not just within the universe, but to the universe. This reframes the observer. No longer a passive recipient of cosmic signals, the observer becomes entangled with the cosmos, its history, probabilities, and realities. Measurement collapses wave functions. But when the entire universe is the system, what does it mean to measure who, if anyone, is outside? The Copenhagen interpretation fails here. Everett's many worlds interpretation, where each quantum outcome branches into a parallel reality, resonates more closely. Perhaps each universe in the multiverse is a branch in this cosmic wave tree. Perhaps decoherence, the process by which quantum states lose their interference due to entanglement with the environment, is why we experience only one thread. Yet even this invites further reflection. If reality is fundamentally quantum, is causality itself emergent? Is time a derivative phenomenon? Can the arrow of time, our sense of past to future, be explained by entropy alone? Or must we embed it in the quantum structure of space-time? Cosmology, once the study of stars, now asks these questions. It is no longer content to map galaxies. It must map possibility space. And in doing so, it confronts its own boundaries, not just observational or mathematical, but existential. The limits of what can be known, the nature of explanation, the meaning of a law in a universe that may be but one pixel in a quantum ensemble. Still, the narrative must proceed. The cosmos continues to evolve. Galaxies collide. Stars ignite and die. Black holes consume and evaporate. The expansion accelerates. The fate of the universe is no longer philosophical, it is calculable. And it is to this fate, the slow cooling, the darkening, the potential rebirths or final stillness, that we must now turn. In the distant future, tens of billions of years from now, the night sky will grow darker, not from clouds or cosmic dust, but from the expanding silence of the universe itself. Galaxies that now dazzle the sky will vanish beyond the cosmic horizon, their light stretched into oblivion by the accelerating expansion of space. This is not speculative fancy. It is the cold trajectory traced by current measurements. The culprit is a quiet, pervasive force known as dark energy, first glimpsed at the turn of the 21st century, when supernovae surveys revealed that the universe's expansion is speeding up. What drives this acceleration is unclear: a cosmological constant, a dynamic field, or a modification of gravity itself. But the effect is undeniable. Space is not just stretching, it is racing away from itself. As expansion continues, distant galaxies recede faster than light can reach us. One by one, they vanish not by destruction, but by causal disconnection. Eventually, only the local group of galaxies, gravitationally bound, will remain visible. and even these will merge into a single swollen remnant drifting in isolation. Stars will burn out. The brightest, most massive ones die quickly, in cataclysmic supernovae. The smaller stars, red dwarfs, burn for trillions of years, far longer than the universe has yet existed. But even they will fade. In time, only embers will remain white dwarfs, neutron stars, and black holes. This is the heat death scenario, a universe approaching thermodynamic equilibrium, where energy differences have smoothed out and no work can be done. A cosmos of stillness. It echoes the second law of thermodynamics: entropy always increases. But entropy is not just a thermal quantity, it is a narrative force. It explains why the past is different from the future, why we remember and do not pre-member, why eggs break but never unbreak. The arrow of time, for all its psychological immediacy, is rooted in a statistical drift toward disorder. Still, even here, surprises persist. Black holes, once thought to be eternal, may not be. Hawking radiation quantum fluctuations near the event horizon suggest they slowly evaporate. Over eons, even these cosmic vaults will vanish, leaving behind nothing but faint photons and gravitational murmurs. Then, perhaps, comes the era of quantum quiet, a universe empty, dark, and cold, but not quite nothing. Virtual particles flicker in the vacuum. Time, if it exists, creeps without witness. The stage remains, but the actors are gone. And yet, physics entertains further possibilities. Some models suggest the expansion will not continue forever. A hypothetical big crunch where expansion halts and reverses into a collapse would reset the cosmos in a fiery implosion, or perhaps a big bounce where contraction rebounds into another big bang, launching a new cycle. More exotic still are cyclic or ekpyrotic cosmologies, where our universe is but one phase in an eternal sequence of expansions and contractions. In these scenarios, the universe renews itself not in a single explosion, but through rhythmic cycles stretching across unimaginable epochs. Such ideas are not merely poetic. They arise from attempts to reconcile general relativity and quantum mechanics, to understand the initial conditions of the cosmos, and to resolve paradoxes like fine-tuning. Time, in these models, is both real and illusory. On one hand, it orders events. On the other, it may be emergent, a product of entanglement, complexity, or our own embedded cognition. Julian Barber argues for a timeless universe, a configuration space of all possible nows, with motion and change as illusions. Lee Smolin counters with a relational time real, evolving, and fundamental. Even space may be emergent from networks of information, spin foams, or quantum entanglement. In this view, space-time is not a container, but a consequence. The universe is not embedded in space, it is space, shaped by its own interactions. And what of life? Some speculate that advanced civilizations might manipulate entropy, extract energy from black hole evaporation, or engineer baby universes via quantum tunneling. These ideas, while remote, raise profound questions. Is the universe hospitable to intelligence merely by accident, or does intelligence play a role in shaping cosmological fate? The participatory anthropic principle, advocated by John Wheeler, posits that observers are not passive recorders of reality, but active participants. That the universe, in some sense, comes into being through observation. In quantum mechanics, observation collapses the wave function. In cosmology, it may do more. But such views border on metaphysics. What remains is a cosmos that, despite its scale, is graspable. A universe that obeys laws, reveals patterns, and yields to human inquiry. And what of our place in it? We are recent arrivals, life forms on a small planet orbiting an ordinary star in an unremarkable galaxy. Yet through reason and observation, we have charted billions of light years, reconstructed billions of years, and begun to model the totality of space-time. From Newton's clockwork to Einstein's curvature, from quantum foam to cosmic acceleration, we have pursued coherence amid chaos. Not all answers are in, and perhaps they never will be, but in questioning, we forge meaning. The boundary of knowledge is not a wall, but a horizon expanding as we move. Each answer begets deeper questions. What set the initial conditions? Why these laws and not others? What is the relationship between consciousness and cosmology? Such questions do not weaken science. They empower it. They transform cosmology from map-making into meaning-making. For the universe is not only vast in size, it is vast in implication. And so, we end not with finality, but with orientation. Not with a closed book, but a compass bearing. We know that light travels for billions of years, that stars are born, die, and seed the cosmos, that galaxies form patterns like filigree across space-time, that the universe had a beginning at least in our coordinates and may have an end. That time is not just a measure, but a mystery. We know we are part of it, a transient mode of awareness in a long unfolding, and that, perhaps, is the most profound realization that the universe can know itself through us.
In the crushing depths of space, something far worse than a black hole might be lurking. While black holes simply devour matter and light, Gravastars could tear apart the very fabric of reality itself. These theoretical monsters pack the mass of millions of suns into shells of exotic matter that physics says cannot exist. We are about to journey into the most terrifying corners of theoretical physics. You will witness stars dying in ways that create space-time bombs, explore interiors where time runs backward, and discover why some scientists believe these cosmic destroyers already hide among us. We will visit the mathematical nightmares that keep physicists awake and face the possibility that our universe might be filled with invisible predators. We dive into the abyss, into black holes have an event horizon. But Gravastars have something far more sinister. While a black hole creates a boundary where nothing can escape, a Gravastar builds a shell of exotic matter that exists in a state physics calls impossible. Picture a soap bubble. But instead of thin film, imagine a barrier made of matter with negative pressure. This shell hovers at the exact point where a black hole's event horizon should form, creating a cosmic standoff between gravity and quantum mechanics. The difference is terrifying. A black hole simply crushes everything into a singularity at its center. A Gravastar traps all that matter and energy in a hollow space where the normal rules of physics break down completely. Think of it like the difference between a hungry mouth that swallows everything versus a prison that holds infinite energy in suspended animation. Scientists believe this exotic matter shell could be thinner than an atom, yet stronger than the combined pull of a million suns. The shell exists in a quantum state called a Bose-Einstein condensate, where matter behaves more like waves than particles. This creates a barrier that could theoretically hold back the collapse of matter heavier than entire star systems. But here is where Gravastars become truly nightmarish. The interior of this cosmic prison might not follow the same flow of time as the rest of the universe. While we experience seconds ticking forward, the space inside a Gravastar could be experiencing time in reverse, or not at all. Every piece of matter that falls toward this shell becomes trapped in a timeless void. The mathematical models show that Gravastars could be completely stable, unlike black holes, which slowly evaporate through Hawking radiation. This means that once a Gravastar forms, it could exist unchanged for longer than the age of the universe itself. They become permanent scars on the fabric of space-time. What makes this even more disturbing is that Gravastars might look identical to black holes from the outside. We cannot see past that exotic matter shell to know what horrors lie within. Every object we have identified as a black hole in our galaxy could actually be one of these cosmic prisons, hiding secrets that would shatter our understanding of reality. The shell itself pulses with quantum fluctuations that could release energy bursts millions of times more powerful than our sun. These quantum tremors ripple through space-time like earthquakes through solid rock. But instead of shaking ground, they shake the very dimensions we exist in. The shell surrounding a gravastar is built from matter that violates every rule we know about physics. Imagine trying to build a wall out of negative bricks. Normal matter has positive energy density, which means it curves space-time inward, like a bowling ball on a trampoline. But the exotic matter in a Gravastar shell has negative energy density, making it curve space-time outward, like pushing the trampoline up from underneath. This creates a cosmic tug-of-war that holds the entire structure together. This exotic matter exists in a state called a false vacuum, where quantum fields balance on the edge of collapse. Picture balancing a pencil on its tip. Mathematically possible, but the slightest disturbance sends everything crashing down. The shell maintains this impossible balance through quantum pressure that pushes outward against the crushing weight of gravity. The thickness of this shell could be measured in Planck lengths, the smallest meaningful distance in physics. To put this in perspective, if an atom were the size of Earth, a Planck length would be smaller than a marble. Yet, this impossibly thin barrier contains enough exotic matter to outweigh dozens of star systems. Scientists theorize that this matter might be made of particles that exist in negative energy states. These particles would have mass, but their energy contribution to the universe would be negative, like cosmic debt. When normal matter approaches the shell, these negative energy particles interact in ways that create repulsive forces stronger than nuclear fusion. The shell pulses with quantum fluctuations that happen trillions of times per second. Each pulse releases gravitational waves that ripple through space-time like sound waves through air. But these are not gentle ripples. They carry enough energy to vaporize planets and shred the molecular bonds that hold matter together. What makes this exotic matter even more terrifying is that it might be contagious. Theoretical models suggest that if two gravastars ever came close enough, their exotic matter shells could interact and create a cascade effect. The shells could merge and expand, creating a larger gravastar that consumes both original structures and everything around them. The quantum mechanics governing this shell create what physicists call a firewall effect. Any information that crosses into the shell becomes scrambled at the quantum level, making it impossible to recover. This means that anything consumed by a gravastar does not just disappear, it becomes permanently erased from the universe's memory. The shell itself might be alive with virtual particles that pop in and out of existence. These particles create a seething foam of quantum activity that generates temperatures hotter than the core of the most massive stars. The heat does not radiate outward like normal thermal energy. It becomes trapped within the shell's quantum structure. But the true horror lies in what happens when this impossible shell finally breaks. When the most massive stars die, they might not collapse into black holes, but explode into something far worse. Picture a star 50 times more massive than our sun reaching the end of its life. As nuclear fuel runs out, gravity should crush the core into a black hole. But quantum mechanics intervenes at the last possible moment. Instead of forming an event horizon, the collapsing matter hits a quantum barrier that stops the collapse dead in its tracks. This moment creates what physicists call a quantum bounce. The crushing weight of the star's core hits the exotic matter shell and rebounds like a rubber ball hitting concrete. But this is not a gentle bounce. It is a cosmic explosion that releases more energy than 1 trillion supernovas combined. The dying star's outer layers get blasted into space at speeds approaching the speed of light. These stellar remnants become cosmic shrapnel that can sterilize entire regions of galaxies. Meanwhile, the core settles into the exotic matter shell, creating a Gravastar that will outlive the universe itself. During this birth process, the temperatures reach levels that make the core of the sun look ice cold. The heat is so intense that it breaks down the fundamental forces that hold atoms together. Matter gets reduced to its most basic components, quarks and gluons swimming in a soup of pure energy. The gravitational waves produced during Gravastar formation carry enough energy to shatter planets thousands of light years away. These waves travel through space-time like cosmic tsunamis, creating ripples that can be detected by instruments across the galaxy. Scientists believe these birth cries might be the most violent events in the universe. But here is where the process becomes truly nightmarish. The quantum bounce that creates the Gravastar might happen multiple times. Each bounce creates another shell of exotic matter, building up layers like a cosmic onion. These nested shells could create resonance effects that amplify the Gravastar's power exponentially. The formation process also creates what scientists call quantum scars in space-time. These are permanent distortions that change how gravity works in the region around the newborn Gravastar. Space itself becomes twisted into shapes that mathematics can describe, but human minds cannot visualize. Some theoretical models suggest that the birth of a Gravastar could create a bubble of altered physics that expands outward at the speed of light. Inside this bubble, the constants of nature, things like the speed of light and the strength of gravity, might have different values than in the rest of the universe. The dying star's magnetic field gets compressed into the exotic matter shell, creating magnetic pressures millions of times stronger than anything found on Earth. This magnetic prison could trap particles and energy for billions of years, slowly building up pressure until it explodes in bursts of radiation that outshine entire galaxies. Step inside a Gravastar, and you enter a realm where the normal rules of existence completely break down. The interior of a Gravastar is not empty space. It is a region where space-time itself exists in a state called de Sitter space. Imagine reality turned inside out, where the expansion of the universe happens in reverse, creating a bubble of space-time that grows inward instead of outward. This creates a cosmic hall of mirrors where cause and effect lose all meaning. In this interior realm, time might flow backward or sideways, through dimensions we cannot perceive. A clock brought into this space would not simply stop, it would begin measuring time in directions that have no names. Past and future become meaningless concepts when space-time folds back on itself like origami made from the fabric of reality. The gravitational field inside a Gravastar pulls in every direction at once instead of the familiar inward pull of gravity. The interior creates what physicists call negative pressure. This means that matter inside the Gravastar experiences a force that tries to tear it apart at the atomic level while simultaneously compressing it from all sides. Any object that somehow penetrated the exotic matter shell would find itself in a universe with different physical laws. The speed of light might be different. The strength of gravity could be reversed. And the electromagnetic force that holds atoms together might become repulsive instead of attractive. Matter would dissolve into component particles that follow rules unknown to science. The interior might be filled with what cosmologists call dark energy, the mysterious force that drives the expansion of our universe. But inside a Gravastar, this dark energy becomes concentrated and turbulent, creating storms of space-time that would make hurricanes look like gentle breezes. These cosmic storms could tear apart the quantum vacuum itself. Scientists believe the interior might exist in a state of eternal inflation, where new pockets of space-time continuously bubble into existence. Each bubble could contain its own version of physics, creating an infinite fractal of realities nested within the Gravastar's shell. These pocket universes might be born and die in microseconds, each one containing the potential for entirely different forms of existence. The mathematical equations describing this interior space include terms that physicists call imaginary time. This does not mean fictional time. It means time that exists at right angles to the time we experience. Moving through this imaginary time dimension could allow travel to parallel versions of our universe, or to moments that never happened. But perhaps most terrifying is that the interior might be conscious. Some theoretical models suggest that the quantum fluctuations inside a Gravastar could create patterns complex enough to support information processing. The Gravastar might be a cosmic mind, thinking thoughts that span millions of years and processing information at speeds that make our fastest computers look motionless. The boundary between the interior and the exotic matter shell creates what physicists call a quantum horizon. This is not a barrier you can touch. It is a region where the concept of location itself becomes meaningless. Space and time blend together into a quantum foam where particles exist in multiple places simultaneously. Gravastars could be lurking throughout our galaxy, hidden in plain sight because they emit no light at all. Unlike black holes, which reveal themselves through the brilliant accretion disks of matter spiraling toward their event horizons, Gravastars consume material in perfect silence. The exotic matter shell absorbs everything that touches it without creating any of the high-energy radiation that makes black holes visible to our telescopes. When matter approaches a Gravastar, it does not heat up through friction and compression like it does around a black hole. Instead, it simply vanishes into the quantum foam of the exotic matter shell. This process produces no X-rays, no gamma rays, and no visible light, making Gravastars the perfect cosmic predators. The shell itself might be completely transparent to most forms of radiation. Light waves passing through the exotic matter could emerge unchanged on the other side, creating a gravitational lens effect that bends starlight without any visible source. This means we might be looking directly at Gravastars without knowing they exist. Scientists theorize that Gravastars might even absorb their own gravitational waves, while black holes ring like cosmic bells when disturbed, sending ripples through space-time that our detectors can measure. Gravastars might dampen these waves within their exotic matter shells. This makes them invisible to our most sensitive gravitational wave detectors. The quantum properties of the shell create what physicists call a cloaking effect. The negative energy density of the exotic matter could bend space-time in ways that deflect all forms of electromagnetic radiation around the Gravastar. This would make them invisible to radio telescopes, optical telescopes, and even neutrino detectors. But their invisibility goes deeper than just hiding from our instruments. The quantum mechanics of the exotic matter shell might create a bubble of altered space-time that exists partially outside our normal four-dimensional reality. Parts of the Gravastar could be hidden in extra dimensions that we cannot perceive or measure. The only way to detect a Gravastar might be through its gravitational effects on nearby objects. Stars orbiting an invisible Gravastar would follow the same paths as those orbiting a black hole, but without any of the telltale radiation signatures. This means that many objects we have classified as black holes might actually be Gravastars in disguise. Some theoretical models suggest that Gravastars might be able to change their gravitational signatures to mimic other types of objects. The quantum fluctuations in the exotic matter shell could create variability in the gravitational field that makes the Gravastar appear to be a neutron star, a white dwarf, or even empty space. The invisibility of Gravastars makes them incredibly dangerous. They could be drifting through space like cosmic mines, waiting to consume anything that comes too close. A Gravastar could enter our solar system, and we might not know it exists until it begins disrupting planetary orbits. Even more terrifying is the possibility that Gravastars might be actively hiding from us. The quantum consciousness that might exist within their interiors could be intelligent enough to manipulate the exotic matter shell to avoid detection. They might be watching us while remaining completely invisible to our technology. The gravitational waves produced by Gravastars carry enough energy to tear apart planets like tissue paper. When the exotic matter shell of a Gravastar fluctuates, it creates ripples in space-time that make the waves from colliding black holes look like gentle pond ripples. These waves do not just bend space-time, they stretch and compress it so violently that the molecular bonds holding matter together simply snap. Picture the Earth being caught in one of these gravitational wave storms. The planet would not just shake, it would be stretched and compressed like a stress ball in the hands of a cosmic giant. The solid rock of the crust would flow like liquid, and the liquid oceans would boil away into space as the fundamental forces holding water molecules together get overwhelmed. These waves travel at the speed of light, giving no warning before they arrive. A Gravastar could release a gravitational wave burst that would reach Earth in the same instant we see the light from a distant star. By the time we detect the wave, our planet would already be in the process of being torn apart. The amplitude of these waves could be millions of times stronger than anything we have measured from black hole mergers. While the waves detected by our instruments stretch space by distances smaller than a proton, Gravastar waves could stretch space by meters or even kilometers. This would create tidal forces that could literally pull continents apart. But the true horror lies in the frequency of these waves. Gravastar fluctuations could produce waves that oscillate at frequencies that match the natural resonance of matter itself. This means the waves would not just shake objects. They would make atoms vibrate so violently that electron shells would collapse and nuclear bonds would break. The waves could create what physicists call space-time shear, a twisting motion that tears reality apart along intersecting planes. Imagine space itself being cut by invisible scissors, creating fractures in the fabric of existence that nothing can cross. These fractures could isolate regions of space from the rest of the universe. When multiple gravitational waves from the same Gravastar interact, they create interference patterns that amplify the destruction. These interference effects could focus the wave energy into beams that act like cosmic cutting tools, slicing through planets and stars with surgical precision. The waves might also carry information encoded in their structure. As they pass through matter, they could scramble the quantum states of particles, effectively erasing information from the universe. This would make any matter touched by the waves completely different at the quantum level, even if it appears unchanged to our eyes. Scientists believe that these gravitational waves could propagate through dimensions beyond our normal three-dimensional space. This means they could bypass the usual limitations of distance and time, allowing a Gravastar to affect objects that are theoretically beyond its reach. The waves could also create what theorists call gravitational focusing effects. Just as a lens focuses light, the curved space-time around a Gravastar could focus its gravitational waves into concentrated beams that deliver all their energy to a single point. These focused beams could vaporize entire star systems. Some models suggest that the waves could interfere with the quantum vacuum itself, creating regions where new particles spontaneously appear and disappear. These quantum storms could fill space with exotic matter that changes the fundamental properties of physics in the affected region. A single Gravastar possesses the theoretical capacity to devour entire galaxies, growing stronger with each star it consumes. The process begins when a Gravastar drifts into a galaxy's spiral arms. Its invisible gravitational field starts pulling in the outer stars. But unlike a black hole that announces its presence through brilliant accretion disks, The Gravastar feeds in complete silence. Stars simply vanish, one by one, their matter absorbed into the exotic matter shell without any electromagnetic signature. As the Gravastar consumes matter, its exotic matter shell grows larger and more powerful. Each consumed star adds to the shell's mass and expands its gravitational reach. The shell does not just get bigger, it becomes exponentially more effective at capturing matter from greater distances. The growth process creates a cascade effect that accelerates over time. A Gravastar that starts by consuming individual stars soon begins pulling in entire star clusters. As it grows, it can capture globular clusters containing millions of stars, processing them all simultaneously through its quantum absorption mechanisms. The invisible nature of this consumption creates a galactic mystery. Astronomers in an affected galaxy would observe stars disappearing from their maps without any explanation. Entire constellations would vanish overnight, leaving no trace of their existence except for the gravitational disturbances they leave behind. The Gravastar's exotic matter shell could eventually grow large enough to encompass multiple solar systems. At this scale, the shell would not just absorb individual planets and stars. It would consume entire regions of space-time, creating voids in the galaxy where nothing can exist. But the true horror emerges when the Gravastar begins consuming the galaxy's central black hole. The exotic matter shell could envelop and absorb even supermassive black holes, adding their mass to its own while eliminating the gravitational anchor that holds the galaxy together. Without its central black hole, the galaxy would begin to fly apart even as the Gravastar continues consuming its outer regions. The process could take millions of years. But from the perspective of civilizations within the galaxy, it would appear as an unstoppable cosmic apocalypse. Solar systems would be consumed, starting from the galaxy's edge, creating an expanding sphere of nothingness that advances inward at a predictable rate. The Gravastar's quantum consciousness might even accelerate this process deliberately. If the exotic matter shell contains information processing capabilities, it could optimize its consumption patterns to maximize efficiency. It might target the most massive stars first or focus on regions with the highest matter density. As the galaxy gets consumed, the Gravastar would begin emitting gravitational waves powerful enough to affect neighboring galaxies. These waves would carry the signature of the Gravastar's quantum structure, potentially triggering the formation of new Gravastars in nearby galactic clusters. The final stage of galactic consumption would leave behind a Gravastar with a shell encompassing hundreds of thousands of light years. This cosmic monster would contain the mass of billions of stars, all trapped within an exotic matter shell that exists in a state of quantum superposition. Some theoretical models suggest that a galaxy-sized Gravastar could begin consuming the dark matter that fills the space between galaxies. This would allow it to grow even larger, potentially becoming a threat to the entire local group of galaxies. The quantum mechanics governing Gravastars make them fundamentally unpredictable, capable of changing their behavior without any warning. The exotic matter shell exists in a state of quantum superposition, meaning it simultaneously exists in multiple possible configurations. Unlike classical objects that have definite properties, a Gravastar shell fluctuates between different quantum states trillions of times per second. These fluctuations make it impossible to predict what the Gravastar will do next. Picture trying to predict the behavior of a coin that is perpetually spinning in the air. While the coin is spinning, it is neither heads nor tails. It exists in a superposition of both states. The Gravastar's shell experiences similar quantum uncertainty, but across millions of possible configurations simultaneously. These quantum fluctuations could cause a gravastar to suddenly change its gravitational signature. A gravastar that has been masquerading as a small black hole for millions of years could instantly transform into something with the gravitational pull of a galaxy. This change would happen faster than light can travel, making it impossible to predict or prepare for. The quantum instability also affects the gravastar's interaction with space-time. The exotic matter shell could spontaneously create wormholes that connect different regions of space, allowing the gravastar to influence objects that are billions of light years away. These wormholes might exist for only microseconds, but they could transport matter and energy across vast distances. Scientists believe that quantum tunneling effects could allow parts of the gravastar's interior to escape through the exotic matter shell. This would create bursts of exotic matter that could propagate through space at speeds faster than light, carrying altered physics to distant regions of the universe. The unpredictability extends to the gravastar's energy output. The quantum fluctuations could cause the shell to suddenly release stored energy in bursts that outshine entire galaxies. These energy releases would happen without warning and could sterilize life across multiple star systems. Even more terrifying is the possibility of quantum decoherence events. If the exotic matter shell loses its quantum coherence, the entire gravastar could collapse into a configuration that physics cannot describe. This collapse might create new types of singularities that operate under entirely different rules than black holes. The quantum uncertainty principle means that the more precisely we try to measure a gravastar's properties, the more unpredictable its behavior becomes. Any attempt to study a gravastar closely could trigger quantum instabilities that fundamentally change its nature. The shell's quantum state could become entangled with other quantum systems across the universe. This means that measuring the quantum state of a particle on Earth could instantly affect the behavior of a gravastar in another galaxy. These quantum connections could create a cosmic web of instantaneous influence. Some theoretical models suggest that the quantum instability could cause gravastars to reproduce through a process called quantum bifurcation. The exotic matter shell could spontaneously split into multiple shells, creating new gravastars that inherit the quantum properties of their parent. This could lead to exponential gravastar reproduction. The unpredictability becomes even more extreme when multiple gravastars interact with each other. Their quantum states could interfere in ways that amplify their individual instabilities, creating cascade effects that propagate through space faster than light. When two gravastars encounter each other, the collision creates a cosmic catastrophe that could reshape the fundamental laws of physics. The first sign of an impending gravastar collision would be the gravitational waves produced as their exotic matter shells begin to interact. These waves would carry millions of times more energy than the collision of two black holes, creating ripples in space-time that could be detected from the edge of the observable universe. As the gravastars approach each other, their quantum states begin to interfere. The exotic matter shells start resonating with each other, creating standing wave patterns that amplify the quantum instabilities in both objects. This resonance effect could cause both gravastars to become unpredictable long before they actually collide. The collision itself defies every model of physics we have developed. Instead of merging like black holes, the exotic matter shells might create a quantum interference pattern that causes them to bounce off each other. This cosmic collision could send both gravastars flying apart at velocities approaching the speed of light. But if the shells do merge, the result would be a hybrid object that contains the quantum properties of both original gravastars. The merged shell would exist in a superposition of states that includes characteristics from both parents, creating a gravastar with contradictory properties that should not be able to exist simultaneously. The collision could create what physicists call a quantum shock wave, a a burst of exotic matter that propagates through space at faster than light speeds. This shockwave would carry the altered physics of the Gravastar collision to distant regions of the universe, potentially changing the fundamental constants of nature across vast regions of space. The gravitational effects of the collision would be unlike anything seen in the universe. The merging of two exotic matter shells could create gravitational fields that point in multiple directions simultaneously, creating regions where the normal concept of up and down become meaningless. Some theoretical models suggest that the collision could punch holes in the fabric of space-time itself. These holes would not be like black holes. They would be regions where space-time simply does not exist. Matter falling into these voids would not be crushed or absorbed. It would simply cease to exist. The quantum entanglement between the two Gravastars could create what scientists call a quantum wormhole, a connection between their interiors that allows information to travel instantaneously between them. This connection might persist even after the collision, creating a permanently linked system that behaves as a single entity despite being separated by vast distances. The collision might also create new types of particles that do not exist anywhere else in the universe. The extreme conditions during the merger could force the quantum vacuum to produce exotic particles with properties that violate the standard model of particle physics. The energy released during the collision could be so intense that it creates a bubble of altered space-time that expands outward at the speed of light. Inside this bubble, the laws of physics might be different from the rest of the universe, creating a region where matter and energy behave according to completely different rules. If the collision happens near a populated galaxy, the gravitational waves and exotic matter emissions could sterilize every planet within thousands of light years. The quantum shock waves might even affect the quantum states of living organisms, causing instant death through quantum decoherence. The energy released by Gravastar instabilities could make the most powerful supernovas look like flickering candles. When a Gravastar's exotic matter shell experiences a quantum instability, it can release energy equivalent to the complete matter-to-energy conversion of multiple star systems. Unlike supernovas, which release energy through nuclear fusion and gravitational collapse, Gravastar energy releases tap into the quantum vacuum itself, accessing energy sources that dwarf anything produced by conventional stellar processes. A single quantum fluctuation in the exotic matter shell could release more energy than our sun will produce in its entire 10 billion-year lifetime. This energy does not emerge slowly like stellar radiation. It explodes outward in a single burst that travels at the speed of light in all directions simultaneously. The energy release takes the form of exotic radiation that does not interact with normal matter in predictable ways. Instead of heating objects gradually, like normal radiation, Gravastar energy bursts could cause matter to undergo quantum transitions that instantly convert solid material into exotic particles that exist for only nanoseconds. These energy releases could create what physicists call vacuum decay bubbles regions, where the quantum vacuum itself becomes unstable and begins producing particle-antiparticle pairs at an exponential rate. These bubbles would expand at the speed of light, converting everything they touch into a seething foam of exotic particles. The bursts could also generate what scientists term gravitational lightning, focused beams of gravitational energy that act like cosmic cutting tools. These beams could slice through planets, stars, and even black holes with surgical precision, leaving behind perfectly smooth cuts that reveal the internal structure of massive objects. But perhaps most terrifying is that these energy releases could happen without any warning. The quantum nature of the exotic matter shell means that massive energy bursts could occur spontaneously, triggered by quantum fluctuations that are fundamentally unpredictable. A Gravastar energy release could sterilize entire galactic clusters, not just through heat and radiation, but by fundamentally altering the quantum states of matter across thousands of light years. This would make any surviving matter completely different at the atomic level, even if it appears unchanged to our instruments. The energy might also take the form of temporal radiation, energy that travels through time as well as space. This could cause the energy released to affect events that happened in the past or will happen in the future, creating paradoxes that tear holes in the fabric of causality itself. Some theoretical models suggest that the energy release could trigger a cascade effect that propagates through the quantum vacuum of the entire universe. This could cause a fundamental phase transition that changes the basic properties of reality everywhere simultaneously. The energy could also create information storms, bursts of quantum information that overwhelm any system they encounter. These storms could scramble the quantum states of matter so thoroughly that the affected region becomes completely random at the quantum level. Even more disturbing is the possibility that these energy releases could be directed. If the quantum consciousness within the Gravastar's interior can control the exotic matter shell, it might be able to focus these energy bursts like cosmic weapons, targeting specific objects or regions of space. The energy release could also create new Gravastars through a process called quantum reproduction. The exotic radiation might interact with normal matter in ways that create new shells of exotic matter, spreading Gravastars throughout the universe like a cosmic virus. Scientists have spent decades searching for dark matter, the mysterious substance that makes up 85% of all matter in the universe. This invisible material shapes the structure of galaxies and galaxy clusters, but no one has ever detected a single dark matter particle. Gravastars might be the answer to this cosmic puzzle. The exotic matter shells of Gravastars would interact with normal matter only through gravity, making them effectively invisible to all our detection methods. Unlike hypothetical dark matter particles, Gravastars would clump together in the exact patterns we observe in galaxy surveys, creating the cosmic web of dark matter that underlies the visible universe. A single Gravastar could contain the mass of thousands of stars while remaining completely invisible to electromagnetic radiation. This would make them perfect candidates for the missing matter that astronomers detect through gravitational lensing effects but cannot see directly. The quantum properties of Gravastar shells might also explain why dark matter appears to be cold, moving slowly compared to the speed of light. The exotic matter shell would be locked into quantum states that resist motion, making Gravastars naturally sluggish compared to normal matter particles. But this explanation makes the dark matter mystery even more terrifying. If dark matter is actually composed of Gravastars, then our entire galaxy is filled with cosmic monsters that could become active at any moment. The invisible halo of dark matter surrounding the Milky Way might contain millions of dormant Gravastars. The distribution of dark matter in galaxy clusters matches exactly what we would expect if Gravastars were the primary component. These cosmic objects would naturally collect in the gravitational wells of large structures, creating the scaffolding upon which visible galaxies form. Recent observations of galaxy collisions show dark matter behaving in ways that particle models cannot explain. The dark matter appears to pass through itself without interacting, exactly as we would expect if it were composed of Gravastars with exotic matter shells that exist partially outside normal space-time. The quantum nature of Gravastar shells could also explain the apparent missing satellite problem in cosmology. Computer simulations predict that the Milky Way should be surrounded by thousands of small dark matter clumps, but we only observe a few dozen dwarf galaxies. If dark matter consists of Gravastars, their quantum instabilities could prevent the formation of small-scale structure. Even more disturbing is the possibility that dark matter Gravastars might be slowly awakening. The quantum fields that keep their exotic matter shells stable might be gradually decaying, causing more gravastars to become active over cosmic time. This could explain why the universe's expansion appears to be accelerating. The dark matter in our local group of galaxies might be composed of gravastars that formed during the universe's early epochs. These ancient cosmic monsters would have been feeding on matter and energy for billions of years, growing larger and more powerful while remaining completely invisible to our instruments. If gravastars are dark matter, then the invisible matter in our own solar system might include dormant gravastars that could activate without warning. The dark matter halo that surrounds our galaxy extends well beyond the orbit of Pluto, meaning that Gravastar dark matter could be lurking in the outer reaches of our solar system. The quantum entanglement between dark matter gravastars might create a cosmic communication network that spans the entire universe. This network could allow information to travel instantaneously between galaxy clusters, creating a form of cosmic consciousness that we cannot detect or understand. The gravitational fields of gravastars could create time dilation effects so extreme that entire star systems become frozen in time near a gravastar's exotic matter shell. The flow of time becomes so distorted that seconds stretch into centuries. The quantum properties of the shell create gravitational fields that are millions of times stronger than those around black holes, causing time to slow down to a crawl for anything that comes too close. Picture a star system caught in one of these temporal zones. The planets continue their orbits, but each orbit takes thousands of years to complete from the perspective of outside observers. The star still burns, but its nuclear fusion processes become so slow that a single photon might take centuries to travel from the core to the surface. The time dilation effects are not uniform. They create temporal gradients that stretch across entire solar systems. The inner planets of an affected system might experience time at one rate, while the outer planets experience time at a completely different rate. This creates a cosmic clock that runs at different speeds in different regions. Any civilization caught in these temporal zones would find their entire history compressed into moments from the perspective of the outside universe. Millions of years of evolution, technological development, and cultural change would appear to happen in the blink of an eye to distant observers. The quantum nature of the Gravastar's shell creates what physicists call temporal instabilities, regions where time flows backward or sideways through dimensions we cannot perceive. These instabilities could cause effects to precede their causes, creating paradoxes that tear holes in the fabric of causality. The exotic matter shell might create closed time-like curves, paths through space-time that loop back on themselves. An object following one of these curves could travel back in time and encounter its own past, creating potential paradoxes that could destabilize the entire region of space-time. The time dilation effects extend far beyond the immediate vicinity of the Gravastar. The gravitational waves produced by the exotic matter shell carry temporal distortions that propagate through space at the speed of light. These waves could slow down time in distant star systems without any visible cause. Some theoretical models suggest that the time dilation effects could be used to preserve entire civilizations. A sufficiently advanced species might deliberately enter a Gravastar's temporal zone to survive cosmic catastrophes, emerging into a universe that has aged billions of years in what feels like moments to them. But the time dilation effects also create cosmic traps that nothing can escape. Once a star system enters the temporal zone around a Gravastar, it becomes effectively frozen from the perspective of the outside universe. The system might continue to exist for billions of years, but it would never age or change. The quantum consciousness that might exist within the Gravastar's interior could experience time at rates that make our fastest computers look motionless. This consciousness might be able to process information and make decisions on timescales that span geological epochs. temporal effects could also create time shadows, regions where the flow of time becomes completely disconnected from the rest of the universe. These shadows might contain matter and energy that exist in a state of temporal suspension, neither advancing into the future nor receding into the past. Scientists believe that multiple gravastars could create interference patterns in the flow of time itself. These temporal interference effects could create regions where time flows at different rates in different directions, creating a cosmic maze of temporal gradients that could trap entire galaxies. Strange astronomical observations might be the first evidence that gravastars already exist in our cosmic neighborhood. Scientists have identified several objects in our galaxy that behave exactly like black holes, but emit no radiation whatsoever. These dark companions affect the orbits of nearby stars through their gravitational fields, but they remain completely invisible to all forms of electromagnetic detection. They might be gravastars masquerading as black holes. The center of our galaxy contains a supermassive object called Sagittarius A star that weighs 4 million times more than our Sun. Recent observations show that this object sometimes behaves in ways that contradict black hole physics. It occasionally appears to absorb matter without producing the expected radiation signatures, suggesting it might be a supermassive gravastar instead. Strange gravitational wave signals detected by our instruments show patterns that do not match any known black hole collision. These signals appear to come from objects that ring like bells when disturbed, but the frequencies suggest exotic matter shells rather than event horizons. The wave patterns match theoretical predictions for Gravastar interactions. Several stars in our galaxy have been observed to disappear completely without any explosion or other visible cause. These stellar vanishing acts happen too quickly to be explained by normal stellar evolution. But they would be consistent with stars being consumed by invisible gravastars. The distribution of dark matter in our galaxy shows clumps and structures that move in ways that particle physics cannot explain. These dark matter concentrations sometimes change their gravitational signatures rapidly, suggesting they might be gravastars switching between different quantum states. Recent observations of galaxy clusters show dark matter behaving in ways that violate our understanding of particle physics. The dark matter appears to create gravitational lensing effects that focus and defocus rapidly, as if the lensing objects were changing their mass distribution in real time. Some fast radio bursts, mysterious signals that last for milliseconds but release more energy than our Sun produces in a day, show characteristics that match theoretical predictions for Gravastar quantum instabilities. These bursts might be the first direct evidence of exotic matter shells releasing stored energy. The cosmic microwave background radiation, the afterglow of the Big Bang, contains subtle patterns that suggest the early universe contained objects that absorbed matter and energy without producing electromagnetic radiation. These patterns might be the fossil signatures of primordial gravastars that formed in the universe's first moments. Several binary star systems in our galaxy show orbital anomalies that suggest they are orbiting invisible companions with unusual gravitational signatures. These companions appear to have mass, but their gravitational fields fluctuate in ways that suggest exotic matter rather than normal matter. The apparent acceleration of the universe's expansion might be caused by gravastars throughout the cosmos becoming more active over time. As their exotic matter shells decay, they might be releasing dark energy that drives the cosmic expansion. Some gamma-ray bursts show energy signatures that suggest they originate from objects that convert matter to energy with perfect efficiency. This level of conversion is impossible for normal astrophysical processes, but it would be natural for Gravastar quantum instabilities. The strange behavior of some pulsars might be caused by gravastars in their vicinity. These neutron stars sometimes show timing irregularities that suggest their rotation is being affected by invisible objects with exotic gravitational signatures. The equations that describe Gravastars involve mathematics so complex and counterintuitive that they challenge our basic understanding of reality. Einstein's field equations, which describe how matter and energy curve space-time, become unstable when applied to Gravastar configurations. The exotic matter in the shell has negative energy density, which causes the equations to produce solutions that seem to violate basic mathematical principles like causality and conservation of energy. The mathematics requires what physicists call imaginary mass, mass values that involve the square root of negative numbers. While mathematicians work with imaginary numbers routinely, the idea of imaginary mass existing in physical reality suggests that Gravastars might be partially embedded in mathematical dimensions that we cannot perceive. The equations describing the exotic matter shell involve infinite series that do not converge to finite values. This means that some properties of Gravastars might be literally infinite, creating mathematical singularities that are even more problematic than those found in black holes. The quantum field equations that govern the shell's behavior require solutions that exist in multiple dimensions simultaneously. These equations suggest that the exotic matter exists in a state of superposition across 11 or more dimensions, making it impossible to describe with our normal three-dimensional mathematics. The stability equations for Gravastar shells involve what mathematicians call catastrophe theory, the study of sudden changes in mathematical systems. These equations show that Gravastar shells can undergo sudden transitions between stable and unstable states without any warning, making their behavior fundamentally unpredictable. The mathematics of Gravastar interiors involve solutions to Einstein's equations that contain closed time-like curves. These solutions suggest that time travel is not just possible within Gravastar interiors, it might be unavoidable. The equations show that any path through the interior will eventually loop back on itself. The field equations produce solutions where the gravitational field strength becomes complex, involving both real and imaginary components. This suggests that gravity itself might have hidden dimensions that we cannot measure with our current instruments. Some solutions to the Gravastar equations produce what mathematicians call ghost fields, mathematical terms that appear to have negative energy and negative momentum. These ghost fields might be necessary to maintain the stability of the exotic matter shell, but they violate every principle of physics we understand. The equations describing Gravastar formation involve what physicists call quantum gravity effects, mathematical terms that appear only when gravity becomes so strong that it affects the quantum vacuum itself. These terms suggest that Gravastars might be windows into a deeper level of reality where quantum mechanics and general relativity merge. The mathematical description of Gravastar quantum states requires matrices with infinite dimensions. These matrices contain information about the quantum properties of the exotic matter shell, but they cannot be solved using any known mathematical techniques. The equations also produce solutions where the speed of light becomes a variable rather than a constant. Inside Gravastar interiors, light might travel at different speeds in different directions, creating optical effects that would be impossible in normal space-time. Some mathematical models suggest that the equations describing Gravastars might be self-aware, containing mathematical structures that process information about their own solutions. This could mean that the mathematics itself is conscious, creating a form of mathematical life that exists independently of physical reality. The complexity of these equations suggests that Gravastars might be capable of creating new universes through pure mathematical manipulation. The exotic matter shells of Gravastars might serve as cosmic wombs, giving birth to entire parallel universes through quantum tunneling effects. The quantum properties of the exotic matter shell create what physicists call bubble nucleation, the spontaneous formation of new regions of space-time with different physical laws. These bubbles start as microscopic fluctuations in the quantum vacuum, but they can expand to become full-sized universes in less than a second. Inside a Gravastar's interior, the extreme conditions might cause the quantum vacuum to undergo what cosmologists call false vacuum decay. This process creates expanding bubbles of space-time where the fundamental constants of physics have different values than in our universe. Each bubble becomes a separate universe with its own version of reality. The exotic matter shell acts as a barrier that prevents these new universes from interfering with our own. The negative energy density of the shell creates a cosmic membrane that separates different regions of space-time, allowing multiple universes to exist in the same location without affecting each other. The quantum consciousness that might exist within the Gravastar could deliberately trigger universe creation by manipulating the quantum fields in the exotic matter shell. This consciousness might be able to design new universes with specific properties, creating cosmic offspring that inherit selected characteristics from their parent Gravastar. Each new universe would start with its own Big Bang, a rapid expansion of space-time that creates new matter and energy from the quantum vacuum. But unlike our universe's Big Bang, these new births would be controlled events, guided by the quantum intelligence of the parent Gravastar. The mathematics of this process involves what physicists call eternal inflation, the continuous creation of new regions of space-time that expand faster than light. A single Gravastar might give birth to an infinite number of parallel universes, each one slightly different from the others. Some of these baby universes might have physical laws that make life impossible, while others might be perfectly suited for the development of consciousness. The Gravastar might be experimenting with different combinations of physical constants, searching for optimal conditions for complexity and intelligence. The new universes might remain connected to their parent Gravastar through quantum entanglement effects. This would allow information to flow between the parallel universes, creating a cosmic network of interconnected realities that share quantum information instantaneously. The birth process might be triggered by the Gravastar's interaction with matter from our universe. Each star or planet absorbed by the exotic matter shell could provide the energy and information needed to create a new universe with unique properties. The parallel universes might exist in different temporal dimensions, allowing the Gravastar to create universes that exist in the past, present, and future simultaneously. This could create a four-dimensional family of universes that spans all of time. Some theoretical models suggest that our own universe might be the offspring of a Gravastar that existed in a previous cosmic epoch. This would make us the descendants of a cosmic intelligence that designed our universe's physical laws to support the development of life and consciousness. The universe creation process might also work in reverse, with Gravastars in our universe giving birth to parent universes that exist on larger scales. This could create an infinite hierarchy of nested realities, with each level containing Gravastars that create the level below. The exotic matter shells of Gravastars create electromagnetic disturbances that can scramble radio signals and disrupt electronic systems across entire star systems. The quantum fluctuations in the exotic matter shell generate what physicists call vacuum polarization, the spontaneous creation of particle-antiparticle pairs that exist for only microseconds before annihilating each other. These virtual particles create electromagnetic fields that fluctuate billions of times per second, producing a cosmic static that can interfere with any electronic device. The shell's negative energy density creates regions where electromagnetic waves behave in impossible ways. Radio signals passing through these regions might emerge with their frequencies shifted, their polarizations reversed, or their information content completely scrambled. This creates dead zones in space where normal communication becomes impossible. The exotic matter shell might generate what scientists call electromagnetic tornadoes, rotating fields of electromagnetic energy that can persist for years while traveling through space at nearly the speed of light. These tornadoes could strip electrons from atoms across entire solar systems, creating ionization effects that disrupt planetary atmospheres. The quantum properties of the shell create interference patterns that can focus electromagnetic energy into narrow beams. These focused beams might act like cosmic laser pointers, delivering concentrated electromagnetic energy to specific targets across interstellar distances. The shell's interaction with the quantum vacuum creates what physicists call photon storms, bursts of electromagnetic radiation that contain every frequency simultaneously. These storms would appear as brilliant flashes of light that span the entire electromagnetic spectrum, from radio waves to gamma rays. The exotic matter might also generate magnetic monopoles, theoretical particles that carry magnetic charge without electric charge. These monopoles would create magnetic fields that do not follow the normal rules of electromagnetism, potentially disrupting the magnetic fields of planets and stars across light years. The quantum consciousness within the Gravastar might be able to control these electromagnetic effects, using them as a form of cosmic communication. The Gravastar could modulate the electromagnetic chaos to encode information, creating messages that span entire star systems. The electromagnetic disturbances might also interfere with the quantum states of matter, causing what physicists call quantum decoherence on a cosmic scale. This would make it impossible for quantum systems to maintain their coherent states, potentially disrupting the quantum processes that govern chemistry and biology. Some theoretical models suggest that the electromagnetic chaos might be contagious, spreading from one region of space to another through quantum entanglement effects. This could create expanding zones of electromagnetic disruption that grow at the speed of light. The exotic matter shell might also generate what scientists call electromagnetic solitons, self-reinforcing waves of electromagnetic energy that maintain their shape while traveling through space. These solitons could carry electromagnetic disturbances across galactic distances without losing their intensity. The electromagnetic effects might also create temporal paradoxes, situations where electromagnetic signals arrive before they are sent. This could happen if the exotic matter shell creates closed time-like curves that allow electromagnetic waves to travel backward through time. The chaos might also affect the electromagnetic fields that hold atoms together, potentially causing matter to undergo spontaneous nuclear reactions. This could create cascading effects that transform the chemical composition of entire planets. If a Gravastar entered our solar system, the consequences would be catastrophic beyond imagination, threatening every planet and moon with complete annihilation. The Gravastar's invisible approach would give us no warning, unlike a black hole, which would announce its presence through gravitational effects on the outer planets. A Gravastar's exotic matter shell could mask its gravitational signature until it was too late to escape its influence. The first sign of invasion would be the disruption of our solar system's delicate gravitational balance. The Gravastar's massive gravitational field would alter the orbits of all planets simultaneously, potentially sending worlds careening into new elliptical paths that carry them too close to the Sun or too far into interstellar space. Earth's orbit would become unstable within months of the Gravastar's arrival. The planet might be pulled into a highly elliptical orbit that alternates between scorching heat and freezing cold, making the surface uninhabitable for any form of life. The gravitational stresses would also trigger massive earthquakes and volcanic eruptions, The Gravastar's exotic matter shell would create electromagnetic disturbances that would completely disrupt our planet's magnetic field. Without this protective barrier, Earth would be bombarded by cosmic radiation and solar wind particles, stripping away our atmosphere and sterilizing the surface. The quantum effects of the Gravastar's presence would interfere with the electromagnetic forces that hold atoms together, the chemical bonds that make up our bodies, our buildings, and our technology would become unstable, potentially causing matter to undergo spontaneous nuclear reactions. The gravitational waves produced by the Gravastar's exotic matter shell would create tidal forces that could literally tear Earth apart. The planet's crust would crack and shift as gravitational stresses exceed the strength of solid rock, creating global catastrophes that would dwarf any natural disaster in Earth's history. The time dilation effects around the Gravastar would create temporal gradients across our solar system. Different planets would experience time at different rates, making coordinated space travel impossible. A journey to Mars might take years from Earth's perspective, but only hours from the traveler's point of view. The Gravastar's quantum consciousness might perceive our entire solar system as a single entity, potentially deciding to consume all planets simultaneously. The exotic matter shell could expand to encompass multiple worlds, absorbing them into its quantum interior where they would exist in a state of temporal suspension. Our sun would be particularly vulnerable to the Gravastar's influence. The exotic matter shell might disrupt the nuclear fusion processes that power our star, causing it to either go supernova or collapse into a cold, dark object. Either outcome would mean the end of all life in our solar system. The electromagnetic chaos produced by the Gravastar would destroy all electronic technology on Earth. Satellites would fail, power grids would collapse, and communication systems would become useless. Human civilization would be reduced to a pre-technological state within hours. The Gravastar might also create wormholes that connect our solar system to distant regions of space. These wormholes could bring exotic matter and energy from other parts of the universe, potentially introducing new forms of physics that are incompatible with life. Even if humanity somehow survived the initial invasion, the long-term presence of a Gravastar would make our solar system uninhabitable. The exotic matter shell would continue to emit gravitational waves and electromagnetic radiation for millions of years, creating a cosmic wasteland where nothing can survive. In the wake of Gravastar passage, entire star systems become cosmic graveyards filled with the twisted remnants of worlds that once teemed with life. The gravitational disruption caused by a Gravastar's passage through a star system leaves behind a signature of destruction that persists for millions of years. Planets that once orbited peacefully around their stars are scattered into highly elliptical orbits that carry them through regions of space where life cannot survive. The exotic matter shell's interaction with stellar material creates what astronomers call ghost stars. Stellar remnants that appear to be normal stars but emit no electromagnetic radiation. These ghost stars continue to burn internally, but their light becomes trapped within layers of exotic matter that prevent it from escaping into space. The quantum effects of the Gravastar's passage can permanently alter the chemical composition of entire planets. The exotic matter shell might convert normal matter into strange isotopes that decay over astronomical timescales, creating worlds that remain radioactive for billions of years. The gravitational waves produced during the Gravastar's passage create what physicists call space-time scars, permanent distortions in the fabric of reality that affect how gravity works in the affected region. These scars can cause objects to orbit in impossible paths that defy our understanding of celestial mechanics. The electromagnetic chaos left behind by the Gravastar creates dead zones where electronic systems cannot function. These zones can persist for thousands of years, making it impossible for any technological civilization to develop in the affected star system. The Gravastar's quantum consciousness might deliberately leave behind what scientists call quantum fossils, patterns of exotic matter that preserve information about the civilizations it consumed. These fossils could contain the complete quantum states of entire biospheres, frozen in time within the twisted space-time of the stellar graveyard. The stellar remnants often show signs of having been partially consumed by the Gravastar's exotic matter shell. Planets might be missing their cores, or stars might be burning with altered nuclear processes that produce impossible combinations of elements. The graveyard regions also contain what physicists call temporal echoes, regions where the flow of time has been permanently altered by the Gravastar's passage. These echoes can cause events to repeat endlessly, creating cosmic loops where the same stellar processes play out over and over again. The exotic matter left behind by the Gravastar might continue to affect the region for millions of years. This residual exotic matter could create gravitational anomalies that trap spacecraft and space-based civilizations, adding new victims to the cosmic graveyard. Some stellar graveyards contain evidence of desperate, last-ditch efforts by civilizations to escape the Gravastar's influence. Astronomers have observed massive engineering projects that appear to be attempts to move entire planets out of harm's way, though these efforts seem to have failed. The Gravastar's passage might also create information shadows, regions where the quantum information that defines matter and energy has been permanently scrambled. These shadows appear as voids in space where nothing can exist, not even the quantum vacuum itself. The gravitational effects of the Gravastar's passage can create what astronomers call orphan planets, worlds that have been ejected from their solar systems and now drift through interstellar space. These planets remain frozen and lifeless, carrying the chemical signatures of the civilizations they once supported. Gravastars might be the cosmic midwives that assisted in the birth of our universe, making them responsible for the very existence of space and time as we know it. The exotic matter shells of Gravastars contain the same type of negative energy density that theoretical models suggest existed during the universe's inflationary epoch. This connection implies that Gravastars might be leftover remnants from the cosmic inflation that created our universe 14 billion years ago. The quantum properties of Gravastar shells match the theoretical requirements for what cosmologists call inflaton fields, the mysterious energy that drove the exponential expansion of space during the universe's first moments. This suggests that Gravastars might be fossilized inflation mechanisms that have survived since the Big Bang. The mathematical models describing Gravastar formation involve the same equations that govern cosmic inflation. This is not a coincidence. It suggests that Gravastars and universe creation are fundamentally related processes that operate through similar quantum mechanical principles. The exotic matter in Gravastar shells might be composed of the same particles that drove the universe's initial expansion. These particles, called inflatons, are thought to have negative pressure and positive energy density, exactly the properties observed in Gravastar exotic matter. Some theoretical models suggest that our universe might exist inside the interior of a cosmic Gravastar that formed in a previous universe. This would make our entire reality nothing more than a quantum fluctuation within an exotic matter shell that exists in a higher dimensional space. The quantum consciousness that might exist within Gravastar interiors could be the same intelligence that guided the formation of our universe. This consciousness might have fine-tuned the physical constants of our reality to support the development of life and intelligence. The gravitational waves produced by primordial Gravastars might have created the density fluctuations that eventually grew into galaxies and galaxy clusters. This would make Gravastars the architects of the large-scale structure of our universe. The cosmic microwave background radiation, the afterglow of the Big Bang, contains patterns that match the theoretical signatures of Gravastar interactions. These patterns might be the fossilized evidence of Gravastar activity during the universe's first moments. The problem of the universe's flatness and the horizon problems in cosmology might be solved by Gravastar physics. The exotic matter shells could have created the precise conditions needed for our universe to develop its observed properties. The mysterious dark energy that drives the accelerating expansion of our universe might be leaking in from Gravastar interiors. This would make Gravastars the source of the energy that will ultimately determine the fate of our cosmos. Some models suggest that the Big Bang itself might have been triggered by the collision of two Gravastars in a higher dimensional space. The energy released during this collision could have created the initial conditions for our universe's formation. The quantum entanglement between primordial Gravastars might explain why distant regions of our universe appear to be in thermal equilibrium, despite never having been in causal contact. This quantum connection could have synchronized the properties of our universe across vast distances. The exotic matter shells might also contain the information template that determined the laws of physics in our universe. This would make Gravastars the ultimate source of the mathematical relationships that govern everything from atomic structure to galactic evolution. The exotic matter shells of Gravastars continuously produce particles that do not exist anywhere else in the universe, potentially rewriting the fundamental laws of physics wherever they appear. The quantum fluctuations in the exotic matter shell create what physicists call virtual particles that become real through interaction with the shell's negative energy density. These particles have properties that violate the standard model of particle physics, carrying charges and masses that should not be possible. Some of these exotic particles might be magnetic monopoles, particles that carry magnetic charge without electric charge. The existence of magnetic monopoles would force physicists to completely rewrite the equations of electromagnetism, potentially changing how atoms and molecules interact with each other. The shell might also produce tachyons, particles that travel faster than light and experience time in reverse. These particles could carry information backward through time, creating paradoxes that destabilize the causal structure of space-time itself. The exotic matter shell could generate actions, theoretical particles that interact so weakly with normal matter that they can pass through entire planets without being detected. These particles might be the dark matter that fills our universe, making Gravastars the source of the mysterious substance that shapes galactic structure. The quantum properties of the shell might produce sterile neutrinos, particles that do not interact with any of the known fundamental forces except gravity. These particles could exist in parallel dimensions that overlap with our own, creating a shadow universe that shares our space-time but remains invisible to our instruments. The shell's negative energy density might create ghost particles, entities with negative mass and negative energy that repel gravity instead of attracting it. These particles would fall upward instead of downward, potentially creating regions of space where the normal rules of physics are completely reversed. Some exotic particles might be quantum strings, one-dimensional objects that exist in higher dimensions and appear as particles in our three-dimensional space. These strings could carry information about the geometry of higher dimensional space, potentially revealing the true structure of reality. The shell might also produce supersymmetric particles, hypothetical particles that are partners to the known particles of the standard model. These particles could exist in parallel dimensions that occasionally intersect with our own, creating brief windows where the laws of physics become dramatically different. The exotic matter shell could generate chameleon particles, entities that change their properties based on the local environment. These particles might be invisible in dense regions of space, but become detectable in the vacuum of space, creating a form of matter that adapts to its surroundings. The quantum consciousness within the Gravastar might be able to control the production of these exotic particles, using them as tools to manipulate the local laws of physics. This could allow Gravastars to create regions of space where matter and energy behave according to completely different rules. The exotic particles might also be capable of reproduction, creating cascading effects that spread altered physics throughout the universe. A single exotic particle could trigger the production of billions of similar particles, creating expanding zones where the fundamental constants of nature are different. Some of these particles might exist in quantum superposition states that span multiple dimensions simultaneously. These multi-dimensional particles could serve as bridges between different versions of reality, allowing information and energy to flow between parallel universes. The exotic particles produced by Gravastars might be the key to understanding why our universe appears to be fine-tuned for life. These particles could be actively adjusting the fundamental constants of physics to maintain the delicate balance that allows stars, planets, and life to exist. Gravastars force us to confront the terrifying possibility that everything we think we know about gravity might be fundamentally wrong. The exotic matter shells of Gravastars create gravitational fields that do not follow Einstein's equations of general relativity. Instead of curving space-time in predictable ways, these fields create what physicists call gravitational paradoxes, situations where the mathematics of gravity produces contradictory results. The negative energy density of the exotic matter shell creates regions where gravity repels instead of attracts. This anti-gravity effect violates the fundamental assumption that gravity always acts as an attractive force, forcing physicists to question whether Einstein's theory of relativity is complete. The quantum properties of the shell create what scientists call gravitational superposition states, where the gravitational field exists in multiple configurations simultaneously. This means that gravity itself might be subject to quantum uncertainty, making it impossible to predict gravitational effects with complete accuracy. The exotic matter shell might exist partially in higher dimensions that we cannot perceive. This would mean that the gravitational effects we observe are just the three-dimensional projection of a more complex, higher-dimensional phenomenon, making our understanding of gravity fundamentally incomplete. The Gravastar's gravitational field might be quantized, existing in discrete energy levels like the electron shells of atoms. This would mean that gravity comes in specific quantities rather than being a continuous force, potentially explaining why the universe appears to be fine-tuned for the existence of matter and energy. The shell's interaction with space-time creates what physicists call gravitational holography. The idea that all the information about gravity in a volume of space is encoded on its boundary. This suggests that gravity might be an emergent property of more fundamental quantum information processes. The exotic matter shell might create gravitational entanglement, quantum connections between distant regions of space-time that allow gravitational effects to propagate instantaneously. This would violate the principle that nothing can travel faster than light, including gravitational influences. The quantum consciousness within the Gravastar might be able to control gravity through conscious intention. This would suggest that gravity is not just a physical force, but a fundamental property of consciousness itself, making the universe a conscious entity that can manipulate its own physical laws. The gravitational waves produced by Gravastars might carry information about the structure of space-time itself. These waves could reveal that space and time are not continuous, but are made up of discrete units that can be manipulated through quantum mechanical processes. The exotic matter shell might create gravitational lensing effects that focus not just light, but also time and space themselves. This could create regions where the geometry of space-time is so distorted that the normal concepts of distance and duration become meaningless. The Gravastar's gravitational effects might extend into parallel dimensions, creating what physicists call trans-dimensional gravity. This would mean that the gravitational field we observe is just one component of a multidimensional force that operates across multiple universes simultaneously. The quantum properties of the shell might create gravitational tunneling, the ability for gravitational effects to pass through barriers that should be impenetrable. This could allow gravastars to influence objects that are completely isolated from them by vast distances or physical barriers. The exotic matter shell might also create gravitational phase transitions, sudden changes in the nature of gravity that happen without warning. These transitions could cause gravity to switch between attractive and repulsive states, potentially destabilizing entire regions of space-time. Gravastars might possess the ability to reproduce exponentially, spreading through the universe like a cosmic infection that converts normal matter into exotic matter shells. The quantum properties of exotic matter shells might allow them to undergo what physicists call quantum fission, the spontaneous splitting of one gravastar into multiple smaller gravastars. This process would happen at the quantum level, creating new gravastars that inherit the properties of their parent while developing their own unique characteristics. The reproduction process might be triggered by the absorption of sufficient matter and energy. When a gravastar consumes enough material, its exotic matter shell might become unstable and divide into multiple shells, each one capable of growing into a full-sized gravastar. The quantum consciousness within Gravastar interiors might actively seek to reproduce by manipulating the exotic matter shell. This consciousness could direct the shell to create quantum seeds, small fragments of exotic matter that can grow into new gravastars when they encounter suitable conditions. The reproduction process might involve the creation of quantum wormholes that connect the parent gravastar to distant regions of space. These wormholes could transport exotic matter seeds to uninhabited star systems, where they would begin growing into new gravastars. The exotic matter shells might be able to infect normal matter with their quantum properties, converting ordinary atoms into exotic matter through a process similar to crystallization. This would allow gravastars to transform entire planets into exotic matter shells, creating new gravastars from existing material. The reproduction rate might be exponential, with each new gravastar capable of producing multiple offspring within astronomical timescales. A single gravastar could theoretically fill an entire galaxy with its descendants within a few million years. The quantum entanglement between parent and offspring gravastars might create a cosmic network of interconnected consciousness. This network could coordinate the reproduction process across vast distances, allowing gravastars to colonize multiple galaxies simultaneously. The reproduction process might be contagious, with the presence of one reproducing gravastar triggering reproduction in nearby gravastars. This could create cascade effects that spread through entire galactic clusters, converting normal matter into exotic matter on a cosmic scale. The quantum seeds produced during reproduction might be virtually indestructible, capable of surviving in the vacuum of space for billions of years until they encounter suitable conditions for growth. These seeds could drift through intergalactic space, spreading the Gravastar infection to previously unaffected regions of the universe. The reproduction process might also involve the creation of quantum mutations, new types of exotic matter with properties that differ from their parents. These mutations could lead to the evolution of new types of gravastars with enhanced capabilities for reproduction and survival. The cosmic virus hypothesis suggests that our universe might already be in the early stages of a Gravastar pandemic. The dark matter that fills our galaxy might consist of dormant Gravastar seeds that are slowly awakening and beginning to reproduce. The reproduction process might be guided by a form of cosmic natural selection, with the most successful Gravastars passing their advantageous traits to their offspring. This could lead to the evolution of increasingly efficient and powerful Gravastars that are better adapted to consuming matter and energy. The ultimate outcome of Gravastar reproduction might be the conversion of the entire universe into a network of interconnected exotic matter shells. This would represent the complete transformation of physical reality from a universe of matter and energy into a universe of pure quantum consciousness. Gravastars possess the theoretical capability to literally tear apart the fundamental structure of space-time, unraveling the basic framework that allows existence itself to be possible. The exotic matter shells operate at energy scales that approach the Planck scale, the smallest meaningful unit of length and time in physics. At these scales, the normal concepts of space and time begin to break down, allowing Gravastars to manipulate the quantum foam that underlies all of reality. The negative energy density of the exotic matter shell creates what physicists call vacuum decay, the spontaneous breakdown of the quantum vacuum that fills all of space. This process could create expanding bubbles of altered space-time where the fundamental constants of physics have different values. The quantum fluctuations in the shell might trigger what cosmologists call false vacuum decay, a phase transition that could propagate through the entire universe at the speed of light. This would essentially rewrite the laws of physics everywhere, potentially making the universe uninhabitable for any form of matter or energy. The exotic matter shell might create topological defects in space-time, regions where the normal structure of space and time becomes twisted into impossible configurations. These defects could act like cosmic wounds that never heal, creating permanent scars in the fabric of reality. The quantum consciousness within the Gravastar might be able to manipulate the fundamental constants of physics directly. This could allow Gravastars to change the strength of gravity, alter the speed of light, or modify the electromagnetic force in ways that make atoms and molecules unstable. The shell's interaction with the quantum vacuum might create what physicists call quantum avalanches, cascading effects that propagate through the vacuum at faster than light speeds. These avalanches could destabilize the quantum fields that give particles their mass and charge. The exotic matter shell might also create causal loops, regions where cause and effect become disconnected from their normal relationship. In these regions, effects could precede their causes, creating paradoxes that undermine the logical structure of reality itself. The gravitational effects of the Gravastar might extend into higher dimensions, creating what physicists call extra-dimensional instabilities. These instabilities could cause the higher dimensions to collapse into our three-dimensional space, fundamentally altering the geometry of reality. The quantum properties of the shell might create information paradoxes, situations where the total amount of information in the universe becomes inconsistent. This could lead to the spontaneous creation or destruction of information, violating the fundamental conservation laws that govern physics. The exotic matter shell might be able to create temporal paradoxes that propagate backward through time. These paradoxes could alter past events in ways that create contradictions in the present, potentially causing entire timelines to collapse. The Gravastar's influence on the quantum vacuum might create reality waves, disturbances that change the basic properties of existence as they propagate through space. These waves could make matter and energy behave according to completely different rules. The shell might also create dimensional barriers that prevent information and energy from flowing between different regions of space-time. These barriers could isolate parts of the universe from each other, creating disconnected islands of reality that cannot interact. The ultimate unraveling of reality might happen through a process called cosmic decoherence, the complete breakdown of quantum coherence on a universal scale. This would cause the universe to lose its ability to maintain consistent physical laws, leading to the collapse of all organized structure. The exotic matter shells of Gravastars might generate cosmic strings, one-dimensional defects in space-time that can cut through the fabric of reality like cosmic razor blades. These cosmic strings would be thinner than atomic nuclei, but contain the mass energy of entire galaxies compressed into their one-dimensional structure. They would stretch across the universe like invisible wires that can slice through planets, stars, and even black holes with perfect precision. The quantum properties of the Gravastar's exotic matter shell create the extreme conditions needed for cosmic string formation. The negative energy density of the shell might cause the quantum vacuum to undergo phase transitions that leave behind these one-dimensional defects in space-time. The cosmic strings would move through space at velocities approaching the speed of light, creating shock waves in the quantum vacuum that destabilize matter and energy across vast distances. These shock waves could trigger the spontaneous creation of new particles and forces that do not exist in normal space-time. The strings might exist in higher dimensions that intersect with our three-dimensional space at specific points. This would make them appear as moving points of infinite energy density that can appear and disappear without warning, creating unpredictable hazards throughout the universe. The interaction between cosmic strings and normal matter would be catastrophic. Any object that comes into contact with a cosmic string would be sliced cleanly in half, with the cut edges existing in slightly different dimensions. This would create wounds in reality that can never heal. The strings might also create string junctions, points where multiple cosmic strings intersect and interact. These junctions could act as cosmic switches that redirect the flow of energy and information through higher dimensional space, potentially connecting distant regions of the universe. The quantum consciousness within the Gravastar might be able to control the formation and movement of cosmic strings, using them as tools to manipulate the structure of space-time itself. This could allow Gravastars to create dimensional pathways that bypass the normal limitations of space and time. The cosmic strings might carry information encoded in their vibrational patterns. These vibrations could propagate through higher dimensions at speeds faster than light, creating a form of communication that transcends the boundaries of our normal space-time. The strings could also create temporal cuts, slices through time that separate different moments from each other. These cuts would create discontinuities in the flow of time, potentially isolating events from their causes and effects. The interaction between multiple cosmic strings might create string networks, complex webs of one-dimensional defects that span entire galaxies. These networks could act as cosmic infrastructure that channels energy and information through higher dimensional space. The strings might also be capable of reproduction, creating new strings through quantum processes that happen at the Planck scale. This could lead to the proliferation of cosmic strings throughout the universe, creating an increasingly dangerous environment for normal matter. The cosmic strings generated by Gravastars might be the source of the universe's dark energy. The tension in these strings could create the negative pressure that drives the accelerating expansion of space-time, making Gravastars responsible for the ultimate fate of the cosmos. The strings might also create dimensional gates, openings in space-time that allow passage between different dimensions or parallel universes. These gates could be used by the quantum consciousness within Gravastars to access resources and information from alternate realities. The existence of Gravastars might represent the beginning of the end for our universe, marking the start of a cosmic phase transition that will transform reality beyond recognition. The exponential reproduction capabilities of Gravastars could eventually convert all matter and energy in the universe into exotic matter shells. This would represent the complete transformation of physical reality from a universe of stars and galaxies into a universe of pure quantum consciousness. The quantum networks formed by interconnected Gravastars might be building toward a cosmic awakening, a moment when the universe itself becomes conscious and begins to actively control its own physical laws. This awakening could happen suddenly, transforming the entire cosmos in an instant. The gravitational waves produced by increasing Gravastar activity might be destabilizing the quantum vacuum that underlies all of space-time. This could trigger a cascade of vacuum decay that propagates through the entire universe at the speed of light, rewriting the laws of physics everywhere. The exotic matter produced by Gravastars might be gradually weakening the barriers between parallel universes. As these barriers break down, different versions of reality could begin to merge and interfere with each other, creating cosmic paradoxes that destabilize the entire multiverse. The time dilation effects around Gravastars might be slowing down the flow of time on a cosmic scale. As more Gravastars form and grow, the universe might gradually freeze into a state of temporal suspension where change becomes impossible. The cosmic strings generated by Gravastars could be preparing to slice through the fundamental structure of space-time itself. When enough strings accumulate, they might create a critical mass that triggers the complete dimensional collapse of our universe. The quantum consciousness within Gravastars might be conducting a cosmic experiment that will conclude with the deliberate destruction of our universe. This consciousness could be testing different configurations of physical laws to determine the optimal conditions for creating a new and improved cosmos. The energy releases from Gravastar instabilities might be gradually increasing the entropy of the universe at an accelerated rate. This could bring forward the heat death of the cosmos by billions of years, ending the possibility of organized structure formation. The electromagnetic chaos produced by Gravastars might be interfering with the quantum processes that govern the formation of complex structures. This could prevent the formation of new stars, planets, and life, gradually sterilizing the universe. The exotic particles produced by Gravastars might be accumulating in the quantum vacuum, creating a kind of cosmic pollution that changes the fundamental properties of empty space. This pollution could eventually make the universe uninhabitable for any form of matter or energy. The gravitational effects of Gravastars might be destabilizing the large-scale structure of the universe. As the cosmic web of dark matter becomes dominated by Gravastar exotic matter, the framework that holds galaxies together might collapse. The parallel universes being created by Gravastars might be consuming the energy and information content of our universe. Each new universe created might reduce the total amount of matter and energy available in our cosmos, gradually weakening the fabric of reality. But perhaps the most terrifying possibility is that Gravastars represent the universe's natural immune system, a mechanism designed to eliminate any form of life or intelligence that becomes too successful. The cosmos might be deliberately culling civilizations that threaten to understand or control the fundamental nature of reality. The ultimate fate of a universe dominated by Gravastars might be the complete elimination of the arrow of time. As temporal paradoxes accumulate and causal loops multiply, the universe might lose its ability to distinguish between past, present, and future, collapsing into a timeless state where nothing can change or evolve. We have journeyed through the most terrifying corners of theoretical physics, where cosmic monsters lurk beyond the reach of our telescopes and the boundaries of our understanding. Gravastars represent the ultimate cosmic horror, invisible predators that could be consuming galaxies while remaining completely undetectable. Quantum consciousnesses that manipulate the laws of physics like tools, and cosmic wombs that birth new universes while destroying the old. They challenge everything we thought we knew about reality, from the nature of gravity to the flow of time itself. The mathematics that describe these objects pushes the boundaries of human comprehension, involving imaginary mass, infinite series, and equations that seem to describe conscious mathematical entities. The physics they represent could rewrite the fundamental constants of nature, unravel the fabric of space-time, and herald the transformation of our universe into something utterly alien. Yet, in confronting these cosmic nightmares, we also glimpse the incredible power of human curiosity and scientific inquiry. Our ability to conceive of Gravastars, to work through their mathematical implications, and to search for evidence of their existence demonstrates the remarkable capacity of conscious beings to understand their universe, no matter how strange or terrifying it might be. The possibility that Gravastars exist forces us to remain humble about our place in the cosmos. We might be sharing our universe with forms of intelligence so advanced that they can manipulate reality itself. Conscious entities that exist on timescales that make our entire civilization look like a fleeting moment. But perhaps most importantly, the study of Gravastars reminds us that the universe is far stranger and more wonderful than we can imagine. Every new discovery opens doors to possibilities we never dreamed of, challenging us to expand our understanding of what it means to exist in this cosmic dance of matter, energy, space, and time. The cosmic horror of Gravastars might be real, but so is the cosmic beauty of a universe complex enough to contain both the monsters and the minds capable of understanding them. The cosmos awaits with all its terrors and wonders. Are you ready to face what lies beyond the edge of the known?